In the summer of 1930, a 24-year-old mathematician forever changed our understanding of truth. Kurt Gödel proved what seemed impossible. In any mathematical system, there exist truths that cannot be proven. This revolutionary idea shook the foundations of mathematics, philosophy, and logic itself. But this was only the beginning. His discoveries led to questions about the nature of time, the possibility of time travel, and the existence of God. Today, we delve into the brilliant and enigmatic world of Kurt Gödel. Part 1. The Incompleteness Theorems. In the summer of 1930, Kurt Gödel was just 24, fresh out of his Ph.D. and deeply engaged with the fundamentals of mathematics. Leading mathematicians of that era were almost celebrating, carried by a wave of optimism. The renowned David Hilbert had big dreams: to establish a rock-solid foundation for all mathematics by identifying a complete and consistent set of axioms. The goal was to create a system where every mathematical truth could be derived through straightforward mechanical steps. This would effectively eliminate uncertainty, confusion, and paradoxes from mathematics. Many believed this vision was within reach. Gödel later talked about how he approached this challenge. He started by exploring the consistency of analysis, focusing on continuous functions and calculus. This journey led him to realize that he needed concepts of truth related to arithmetic, the math of basic number operations, to verify the axioms of analysis. This was an unexpected insight. The connection between truth and proof, what is true versus what can be demonstrated as true, became his central interest. In a few short months, Gödel made a groundbreaking discovery that took the mathematical world by surprise. He presented his findings at a conference in Königsberg in September 1930. Not everyone caught on immediately, but John von Neumann, one of the few who understood, was reportedly up all night contemplating it after Gödel's talk, and quickly came up with the second incompleteness theorem. Gödel's findings are known as the first and second incompleteness theorems. Let's break them down without diving into complex math. The first incompleteness theorem suggests this: if you have a consistent formal system that can handle basic arithmetic, it will inevitably be incomplete. In simple terms, there will be truths expressible in that system's language which can't be proven within the system, regardless of how many axioms you add or how ingenious your rules are. If the system handles basic arithmetic and remains consistent, it can't prove all truths about numbers. The second incompleteness theorem takes it a bit further. Such a system cannot prove its own consistency. Essentially, if your mathematical system is consistent, it can't use its own tools to confirm its consistency. This implies that mathematics can't fully validate itself from within. These ideas are profound yet abstract, so let's look at their significance. Gödel's proof is a brilliant display of self-referential logic. He showed how to encode statements about a formal system inside that very system using its symbols. This process, known as Gödel numbering, assigns unique numbers to each symbol, formula, and proof in the system. By doing this, statements about proof become statements about arithmetic, making the whole approach work. Gödel found a way to make math essentially reflect on itself. Using this technique, he crafted a specific sentence, let's call it G, which asserts it cannot be proven within the formal system. Consider this. If the system can prove G, then G would be false, which implies the system is wrongly proving a falsehood, and thus it's inconsistent. If the system is consistent, then it can't prove G, meaning G is indeed true. This shows there are truths the system can't prove. Therefore, it's incomplete. This relates to the liar's paradox, like saying, "I'm lying," but Gödel's design carefully avoids the typical paradox by situating truth and provability in different realms. The Gödel sentence is not a paradox. It's simply a truth that's unprovable within its own system. The assumptions behind Gödel's proof are crucial. His results apply to formal systems that are both consistent and sufficiently powerful, meaning the system does not contradict itself and can handle basic numerical and arithmetic facts. Most foundational mathematical systems meet these criteria. Gödel's theorems cover areas like piano arithmetic and set theory, along with any mathematical systems that professionals use seriously. One big surprise that shook the math world was understanding that Hilbert's program couldn't be achieved. There would never be a complete and consistent set of axioms for all of mathematics. No finite collection of basic principles could ever capture every mathematical truth. The dream of reducing mathematics to just a step-by-step process where every problem could be solved using specific algorithms was shattered. Math would always need a bit of creativity, insights, and new ideas beyond what any fixed system could churn out. But the impact went even further than just the technical side of things. Gödel's theorems gave us a lot to think about regarding the connections between truth and proof, knowledge and formal systems, and what's out there versus what we can actually verify. Consider what it means for truth to go beyond what's provable. We can see the Gödel sentence is true, even if the formal system can't prove it. This realization comes from using informal reasoning that goes outside the system's limits. We rely on our understanding of what the system can and can't do to see why G must be true. This suggests human intuition in math includes pieces that can't be fully captured by any fixed set of rules. The second incompleteness theorem is just as impactful. A mathematical system can't declare its own consistency. To show your axioms are solid, you'd need to step outside them and rely on stronger assumptions. This creates a kind of hierarchy. You can prove one system's consistency within a more powerful system, but that system faces the same problem. There's no ultimate foundation, no basic platform where math can confirm its own coherence without looking elsewhere. Some philosophers and mathematicians found this frustrating, while others thought it was liberating. The idea that math has endless depth, with many truths still out there, unreachable by our current methods, means math will always need human creativity and never become just a finished task. Now, let's look into the connection between Gödel's theorems and his philosophy, mainly his mathematical Platonism. This link is vital, but often misunderstood. Platonism in math suggests that mathematical things and truths exist independently from human minds and formal systems. Numbers, sets, functions. These aren't just things humans made up or tools for us to work with. They're real, existing in an abstract realm. So, doing math is like discovering truths about that world. Mathematical truth isn't based on conventions or constructed ideas. It's seen as objective. Gödel was openly a Platonist for most of his life. He believed math was following a reality, as real as the physical world, just more abstract, and his incompleteness theorems seem to support this view, at least from his perspective. Here's the connection. If math were just about formal systems and mathematical truth simply meant what could be proven within a specific framework, the incompleteness theorems would be interesting, but not philosophically huge. They'd just show that different systems have different abilities. That's it. But if mathematical truth exists on its own, apart from any system, these theorems reveal something much deeper, going beyond any fixed rules. Truth goes beyond proof. The world of math is richer than any structured approach can fully cover. Gödel made this argument clear in his philosophical writings, insisting that his theorems showed mathematical truth can't be limited to just what can be formally proven. There are arithmetic truths that are genuinely true, even if a particular formal system can't prove them. This gap between truth and proof only makes sense if mathematical truths exist beyond human-created systems. Those who question Platonism ask, if you don't buy into an independent realm of mathematical truths, how do you make sense of Gödel's achievements? One way to approach this without jumping into truth claims is to suggest that any consistent formal framework will have some statements it can't prove or disprove. This concept is known as undecidability. Without claiming those undecidable statements are definitively true or false, we can simply point out that sentence G can't be resolved within system S. However, Gödel wasn't on board with this kind of thinking. He believed that the truth of Gödel's sentence can be grasped through informal reasoning, recognizing what the formal system can and can't achieve, a type of intuition. This intuition lets us perceive mathematical truths beyond mere rule following. If our intuition finds truths untouched by formal systems, it means we tap into mathematical realities without relying solely on procedural methods. This debate continues to this day, although formalists, constructivists, and other skeptics have developed advanced opposing views. Gödel's take remains significant. Many mathematicians lean toward Platonism, often unconsciously, feeling they're discovering, not just inventing. Gödel offered philosophical and mathematical backing for this sense. Let's jump into some examples and uses of the incompleteness theorems for better understanding. A prominent undecidable statement is the continuum hypothesis, which concerns the sizes of infinite sets. Cantor showed that different infinities exist. The natural numbers, like 1, 2, 3, etc., form an infinite set, but the real numbers, all possible decimals, represent a bigger infinity. The continuum hypothesis questions whether there's a set size between these two. Is there a set larger than the natural numbers, but smaller than the real numbers? In 1938, Gödel created a mathematical framework called the constructible universe L, where this hypothesis holds true. Then, in 1963, Paul Cohen discovered that other mathematical universes exist where the hypothesis doesn't hold. These findings indicate that the continuum hypothesis is independent of the usual set theory axioms, making it undecidable within ZFC, the Zermelo-Fraenkel set theory with the axiom of choice. Though this isn't directly tied to Gödel's incompleteness, theorems, since the continuum hypothesis isn't about arithmetic, it showcases similar conundrums. Essential questions can remain undecidable within standard foundational systems. Consider another example, the halting problem from computer science. Building on Gödel's work, Alan Turing proved that there's no algorithm to decide if any given computer program and input will stop or run forever. This undecidability arises from the same kind of self-referential logic Gödel employed. If you could figure out the halting problem algorithmically, you'd be able to solve Gödel's sentence, which can't be done. Thus, the halting problem is a computational reflection of incompleteness. You'll also find naturally undecidable statements across math's various fields. Take Gödelstein's theorem, dealing with sequences of natural numbers, which is true but can't be proven in piano arithmetic. Likewise, Kruskal's tree theorem, crucial in computer science and combinatorics, can't be proved in standard systems, but can be in stronger ones. These aren't just hypothetical quandaries. Mathematicians are genuinely invested in questions beyond the reach of certain formal systems. The philosophical takeaway here is that incompleteness isn't merely a glitch or peculiarity in our foundational frameworks. It's an inherent feature of mathematics itself. Any consistent system that's robust enough for substantial work will naturally have its blind spots and unreachable truths. This reality shapes how we comprehend mathematical knowledge, the limits of computation, and the nature of formal reasoning. Let's dive into the big critiques and debates about the incompleteness theorems. Not everyone sees things the way Gödel did or even believes his findings are that important. Some critics, especially strict formalists, completely reject Platonism. They argue that math is all about exploring formal systems and what they lead to. For them, truth only makes sense within these systems, so calling something truly true but unprovable doesn't work. From their view, Gödel just pointed out that no single formal system can cover all of math, and there's always room to move to stronger systems. Math involves creating and understanding different formal frameworks, and it's never-ending. Incompleteness doesn't mean truth is always just out of reach. It's more about the vast range and complexity of mathematical systems out there. This formalist angle has some logic, but Gödel thought it missed the crucial part. If math is just formal games, why do mathematicians obsess over consistency? Why is it so important that ZFC stays consistent and not the opposite? Consistency seems to indicate something real, like whether the axioms describe a logical math world, nudging us back towards realism. Another hot-button issue is whether Gödel's results say something about our brains. Some philosophers, like J.R. Lucas and later Roger Penrose, argued that incompleteness shows that human minds aren't just machines. The idea is that computers are like Turing machines, which are formal systems. So if our minds were just formal systems, they'd be limited by Gödel's theorems. But humans can understand the truth about Gödel's sentences that are beyond any formal system. This implies our minds can't be just formal systems, which means strong AI can't exist, and hints that our thinking might include non-algorithmic aspects, maybe involving quantum processes in the brain. This argument stirred up a lot of debate. The main counterpoint is that it mixes up what a system can prove on its own and what we can learn from an outside view. When we recognize a Gödel sentence as true, we're using informal reasoning about what a system can do, not working within it. A smart enough computer could also study other computers and spot statements they can't verify. The fact that we understand truths about formal systems doesn't prove we aren't formal systems. It just shows we can think on different planes. Penrose suggested that our mathematical intuition involves directly grasping truths, which can't be algorithm-driven. He proposed that we access mathematical reality through a capacity not linked to rule following, potentially involving quantum processes in the brain's microtubules influencing consciousness. Despite this, most philosophers and neuroscientists see this idea as speculative and unnecessary, since no evidence connects quantum effects to everyday thinking. Plus, linking Gödel's theorems to quantum consciousness involves several logical jumps. What did Gödel think about minds and machines? That's interesting. He wasn't convinced human reasoning could be fully automated, but for different reasons than Lucas and Penrose. Gödel believed human math intuition lets us access truths beyond any formal system. This intuition is non-algorithmic, but also isn't mysterious or quantum-based. It's a rational skill to comprehend concepts and their links. This skill's strength, according to Gödel, implied we're likely not equivalent to Turing machines. But he didn't claim this as a proven fact, just a philosophical stance based on his Platonism and rationalism. There are other intriguing angles to think over. Incompleteness has popped up, not always accurately, in discussions about science's limits, truth in ethics and metaphysics, legal reasoning foundations, and even theology. It's important to sort out the valid uses from the overextensions. In science, incompleteness hints that no limited set of laws could explain every true statement about the universe if the universe encodes arithmetic structures. Though, that's a stretch. Physical reality might not behave like a formal system. If the laws of physics can be represented mathematically, there might be questions about the universe that the laws themselves can't resolve. Some physicists have even suggested that issues in quantum gravity or cosmology might be formally undecidable. When it comes to ethics and metaphysics, things get more complicated. Some folks argue that the idea of incompleteness means moral truths can't be neatly organized, or that big metaphysical questions don't have definite answers. But Gödel's theorems are about formal systems, particularly those that encompass arithmetic. We might not be able to put moral reasoning into a nice, tidy system. And even if we could, the fact that a system can't solve a problem doesn't mean there's no truth hidden in there. It just might require thinking beyond that system to find it. Gödel was quite keen on the notion of objective truth, confident that answers to the most pressing questions exist, even if they're still waiting to be found. In religious debates, Gödel's ideas have been used both to defend and challenge beliefs. Some say his work shows that pure reason isn't enough on its own, suggesting a need for divine insight or faith. Others see it as highlighting the boundaries of formal theology. While Gödel was a believer with complex views on faith, he didn't believe his theorems outright proved anything about God. For that, he developed a separate line of reasoning, which we'll explore later. A common misunderstanding of Gödel's work is thinking incompleteness means it's a free-for-all, or that there are no objective truths. This isn't right. What Gödel showed was that truth extends beyond what any single formal system can establish as true. This only holds water if we accept that objective truth really exists. Incompleteness isn't saying there's no truth. It's telling us that formal systems can't capture all of it. Now, let's jump into a thornier issue, the idea of absolutely undecidable statements. These would be statements where you can't determine their truth or falsehood with either formal logic or informal reasoning. Gödel's theorems show undecidability in some systems. But what if some statements are just naturally truthless? Gödel wasn't having any of that. As a Platonist, he figured every properly formed math statement had to be either true or false, even if we never know which. The Gödel sentence is either true or nothing, no wishy-washy middle ground. The continuum hypothesis is a clear-cut truth or falsehood in the math realm. Even if it stands outside ZFC, we just might not have a clue which way it leans yet. Not everyone buys into this take. People like intuitionists and constructivists believe that mathematical truth depends on being able to show a proof. To them, an absolutely undecidable statement wouldn't hold much weight because it wouldn't have a truth value. These differing opinions spark major debates in philosophical circles about the nature of truth and whether it can exist independently of proof or understanding. Gödel's incompleteness theorems haven't really changed the way most mathematicians do their everyday work. Usually, mathematicians keep going without losing sleep over undecidable statements, since they're either rare or related to foundational issues. Most standard math problems get sorted out within the current systems. But Gödel's theorems did change how mathematicians think about the foundations of their field. There's this underlying notion that mathematics stands on assumptions that can't be fully proved from within, showing that the math world never ends. On the other hand, Gödel's work has had a huge impact on mathematical logic, set theory, and computer science, opening doors for ideas about recursive functions and what can be calculated. It sparked interest in different axiom systems and their capabilities. Plus, it raised questions about what can be computed while nudging areas like algorithmic information theory and artificial intelligence forward. Gödel's ideas have really opened up new paths of exploration. Lastly, there's the question of whether we truly get the philosophical heft of incompleteness. Even decades after Gödel's proof, people are still digging into what it means. Is it proof of limits to human reasoning, or does it suggest unbounded potential? Does it support the idea of Platonism or challenge it? Does it speak to something deep about consciousness, or is it just about mathematical logic? These questions stick around, highlighting the lasting impact and depth of Gödel's groundbreaking breakthrough from 1930. In Part 2, we dive into mathematical Platonism and the notion that concepts are actual things. Kurt Gödel thought numbers weren't physical objects we can touch, nor were they just brain activity or marks on paper. Instead, he saw them as real entities in an abstract realm with their own characteristics, distinct from human notions. This idea, known as mathematical Platonism or realism, formed the core of his entire philosophical stance. Everything he pondered about math, logic, knowledge, and truth stemmed from this belief. But what does it actually mean to say numbers or sets are real when they're obviously not tangible? How do we know anything about things that exist outside space and time? And if math involves uncovering truths in this independent realm, how do we perceive these truths? Throughout his life, Gödel wrestled with these questions, and his resolutions reveal a deep philosophy that extends beyond basic Platonism. Let's clarify Gödel's take on Platonism. He explicitly outlined it in various works and discussions. In his 1951 Gibbs lecture, he described realism or Platonism as the belief that mathematical objects and facts exist independently of human thoughts or actions. Mathematical truths aren't crafted by mathematicians, they're discovered. When we prove the Pythagorean theorem, we're not inventing a relationship between a triangle's sides. We're discovering a truth that existed long before humans and would remain valid even without minds. This idea might seem obvious to many mathematicians who often view their work as exploring a pre-existing landscape, but it sparks philosophical debate. The main counter-theories are formalism, which sees math as the study of formal symbols without connection to an external reality, and constructivism or intuitionism, which posits that mathematical objects are mental creations, with truths depending on what mathematicians can prove or create. Gödel disagreed with both these views. Regarding formalism, he pointed out that mathematicians seek consistency and truth, not just symbol manipulation. Axioms aren't chosen randomly. They are selected because they're believed to truthfully reflect mathematical reality. In terms of constructivism, he thought that confining truth to what can be constructed or proven was a limitation. Many mathematical truths exist that might never be proven, but that doesn't mean they aren't legitimate. Gödel found that idea to be nonsensical. Gödel's Platonism didn't stop at objects. It extended to concepts, which is a crucial point often overlooked. He argued that mathematical concepts themselves have an objective reality. The ideas of sets, numbers, functions, they're not just human creations, but objective realities perceived through intuition. This focus on concepts, beyond just objects, gave Gödel's Platonism a distinctive angle. It connects to his interest in phenomenology, which we'll touch on later. For now, grasp that concepts are, in some ways, more basic than individual objects. Understanding a set concept helps us reason about all sets, not just particular ones. Mathematical knowledge comes from refining and investigating concepts. Now, let's explore Gödel's reasoning for Platonism. He didn't just propose it, he tried to explain it logically. His main arguments appeared in the Gibbs lecture and his 1940s papers on set theory. They went something like this: consider how mathematics functions. Mathematicians propose axioms, deduce theorems, and create theories. They don't pick axioms at random. They choose those that resonate with our intuitive understanding of the mathematical domain they're exploring. For example, the axioms of set theory define our intuitive notion of a collection. If any axioms lead to inconsistencies or contradictions, mathematicians adjust them. This makes sense only if there's an objective reality these axioms aim to reflect. We modify our axioms when they don't accurately represent mathematical reality. Moreover, think about how mathematical concepts have evolved and clarified over time. Take the concept of a number, once a rather unclear idea. Over time, math has become more precise. We've figured out various kinds of numbers: natural, integers, rationals, reals, and complex, each one expanding on the last. This evolution feels more like a scientific breakthrough than just creating something from thin air. Mathematicians are like adventurers, slowly detailing a map of a complex terrain. Gödel also highlighted how math often sheds light on real-world happenings. Mathematical structures, initially seen as purely theoretical, often turn out to closely model our universe. For example, non-Euclidean geometry, once just an academic exercise, became essential for grasping general relativity. Similarly, complex numbers, once considered bizarre, are vital in quantum mechanics. This suggests that math isn't just a mental exercise, but might actually describe objective realities present in nature. Gödel's incompleteness theorems added weight to this notion. He proposed that truth extends beyond what we can prove. Mathematical truths can't be fully captured by any formal system. This view makes sense if truth exists independently of our methods of discovery. If truth was only what we could prove, incompleteness would make math uncertain. But if truth is objective, it just highlights our limited tools, not any flaw in truth itself. Despite these reflections, Gödel admitted he couldn't decisively prove Platonism. He shared this frustration with philosopher Hao Wang. The most he could do was reject competing ideas like formalism, constructivism, and nominalism as insufficient. If every other theory is flawed, the remaining one has to be correct. Yet, this didn't fully satisfy him because he couldn't be sure he had considered every possibility. This leads us to Gödel's debated view on mathematical intuition. If abstract math objects are real, how do we comprehend them? We can't physically see or touch numbers or conduct experiments on math concepts, yet mathematicians grasp this abstract realm. Gödel believed intuition, the ability to understand math truths straight away, was crucial. But intuition can sound mystical, implying special abilities or inexplicable insights. Gödel was aware of this and aimed to present intuition in a more scientifically acceptable way. Not everyone was convinced, but his ideas were more sophisticated than critics often acknowledged. Gödel didn't think of math intuition as a magical sixth sense. It's about grasping concepts and knowing their properties. When mathematicians understand what a set or continuity is, this understanding is intuition for Gödel. It's not about memorizing, it's about an immediate intellectual understanding of a concept's essence. Gödel compared mathematical intuition to sensory perception, not because they're identical, but because both connect us with reality. Just like sight gives us direct knowledge of physical things, math intuition provides direct awareness of abstract entities. Both are flawed. One might misperceive a physical object or misinterpret a math idea, but both offer a link to objective reality. This analogy with perception is fundamental to Gödel's view. He believed, much like perception evolved for survival, mathematical intuition evolved to comprehend aspects of abstract reality crucial for rational thinking. Clarifying math concepts is similar to refining our view of the physical world. Critics pounced on this idea. Physical perception involves interactions between objects and senses, like when light hits the retina and triggers a series of events resulting in sight. However, abstract entities aren't involved in causal relationships. They exist outside space and time, untouched by physical interactions. How can we even begin to understand these concepts? This is the big question for Platonism when it comes to mathematical knowledge, leaving it feeling like an unsolvable mystery. Gödel offered some answers, though he didn't fully solve the problem. First, he questioned whether knowledge truly has to come from causal interactions. Why assume all knowledge comes from causal links? It seems like starting from the premise that knowing abstract objects is impossible. Then he suggested that perhaps the mind connects to abstract reality through an intentionality that isn't causally typical, but still allows cognitive access. This ties into his interest in phenomenology, which looks at how consciousness targets objects. Lastly, Gödel argued that the mystery surrounding mathematical knowledge is as perplexing as that of any other kind of knowledge. Even understanding physical objects presents philosophical hurdles. How do brain patterns lead to awareness of the external world? How do personal experiences link to objective reality? These queries aren't limited to math. They apply to all knowledge types. If we can't solve them generally, it's unfair to criticize Platonism for mathematical knowledge facing similar issues. Still, many philosophers found Gödel's intuition-based answers lacking. Without a clear method for distinguishing insights from errors and discerning when intuitive judgments are reliable, intuition seems to place mathematical comprehension on unstable footing. This criticism was powerful, and Gödel wrestled with it during his philosophical career. Notably, Gödel distinguished between different intuitions, one concerning specific objects or facts, and another about concepts and their relationships. The latter is more important. We don't understand numbers individually. We grasp the concept of numbers as a whole and reason from that understanding. This conceptual intuition gives mathematics its structure, not just a jumble of individual insights. Gödel also believed that mathematical intuition could improve with intellectual effort. It's not a static talent that some have while others don't. Through engaging with math, contemplating concepts, and solving proofs, mathematicians enhance their intuitive grasp of mathematical truth. Thus, intuition doesn't precede mathematical reasoning, but grows alongside it. This leads us to questions about mathematical practice that Gödel examined in his work. If math is about discovering truths in an objective realm, what's the role of axioms? How do we justify introducing new axioms? And what if differing axiom sets conflict? Gödel argued that axioms should be immediately graspable. They should seem true when related concepts are clearly understood. For instance, the axioms of set theory should reflect our innate understanding of what sets are. When we say that for any property, there's a collection encompassing all things with that property, it seems apparent given the concept of sets as groups. If this results in paradoxes, we revise our perspective. Perhaps unrestricted comprehension was never truly part of the genuine set concept. This suggests that axioms aren't arbitrary choices for simplicity. They're attempts to formalize our intuitive views of mathematical constructs. Strong axioms accurately depict their intended domains, while weak ones misrepresent or inadequately capture the structures in question. But things get complicated here. Gödel believed some mathematical truths can't be settled by today's axioms. Take the continuum hypothesis. It's independent of standard set theory. Still, Gödel thought it had a definite truth value. Either there's a size of infinity between natural and real numbers, or there isn't. This is an objective fact about the mathematical universe, even if current axioms don't decide it. So how do we find such truths? Gödel believed we'd need new axioms, not just any haphazard additions, but ones that define new dimensions of mathematical reality that present axioms miss. He figured that by exploring and clarifying what we mean by set, we could uncover some basic truths. This links to his work on large cardinal axioms, which we'll dive into later. For now, let's take a look at the philosophical side. Math progresses through a cycle of intuition, forming axioms and refining ideas. We initially grasp mathematical concepts through intuitive feelings. From there, we express this understanding in formal axioms. We learn to apply these axioms practically. Sometimes we find out our axioms were flawed or caused inconsistencies, so we tweak them. Other times, they don't solve every issue, leading us to create new ones. This continuous journey aims to align our formal mathematical systems with the real-world math truths we instinctively feel. Now, let's explore how Gödel's version of Platonism stands out from other kinds of mathematical realism. Over time, philosophy has seen many takes on Platonism, and Gödel had his own distinct spin. Traditional Platonism, based on Plato's ideas, talks about a perfect world of forms or ideas that our physical world merely mirrors. Numbers, like the number 3, belong to these forms. They exist perfectly and eternally in that realm, while physical groups of 3 are imperfect versions. We come to understand these mathematical objects through pure reason, beyond sensory experience. Gödel's Platonism also supports abstract objects existing independently of human minds, but it's less mystical, placing more emphasis on classic Platonism. He wasn't very concerned with how abstract forms relate to their physical counterparts. Instead, he focused on our understanding of mathematical structures through thought and logical intuition. Influential figures like Frege and Russell in the early 1900s came up with logicism, blending Platonism with the idea of math boiling down to logic. They believed mathematical truths were basically logical truths, and mathematical things were logical entities. Gödel disagreed, arguing that you can't reduce math to just logic, as concepts like set or number aren't purely logical. Math covers different ground from logic, though they're closely linked. In more modern times, post-Gödel, structural realism has become more popular in mathematical realism, suggesting mathematical entities represent positions within a framework rather than standalone objects. What's important isn't the essence of the number 3, but its place in the sequence of natural numbers, a viewpoint Gödel might have found interesting but insufficient. Structures themselves are abstract and must objectively exist for realism to make sense. Another approach is mathematical naturalism, trying to combine Platonism with naturalism by explaining our mathematical understanding through natural cognitive processes. Perhaps evolution has tuned our brains to notice abstract patterns, making real-world navigation easier. Gödel likely would have been skeptical, as he didn't think you could fully explain mathematical understanding through natural processes. Our grasp of vast concepts, like the infinite nature of numbers, suggests that our mathematical insights exceed what evolution alone can account for. This leads us to the biggest issue for mathematical Platonism, its epistemological challenge mentioned earlier. If mathematical entities exist beyond time and space without causally interacting, how do we know them? Nominalists and empiricists have critiqued this for ages, and it's a key reason many reject Platonism. Philosopher Paul Benacerraf famously captured this critique in 1973, arguing that a solid theory of mathematical knowledge must show how mathematical beliefs truthfully align with mathematical facts. For ordinary knowledge, this alignment is explained by cause and effect. I think there's a tree up ahead because it triggers certain sensory inputs. But abstract things can't cause anything. So what ties our beliefs about math to actual math facts? Without an explanation, Platonism turns our understanding of math into either a lucky guess or an unsolvable puzzle. Platonists have tossed around a few ideas to solve this. Some say there doesn't need to be a direct cause and effect link for knowledge to exist. Maybe understanding comes from non-causal ways, like having a rational insight or grasping ideas deeply. Others suggest the link between beliefs and facts is because both obey logical and conceptual rules. For instance, we can't logically conclude 2 + 2 = 5 because it doesn't fit with how addition works. The inherent logic in math concepts makes sure our thoughts align with math reality if we think things through clearly. Gödel had a view that involved using intuition conceptually and compared this to how we perceive things. He didn't consider the problem of understanding math as any different from understanding anything else. Every form of knowledge deals with how our minds relate to the real world. This is a big topic in the philosophy of mind and knowledge, but it isn't solely a Platonism problem. Some modern philosophers have come up with what are called indispensability arguments, supporting the reality of math. Basically, math is crucial for our top scientific theories. Physics couldn't be done without relying on math structures. If we trust science to explain reality, then we should also trust the math it uses. Gödel didn't have this exact line of reasoning available, but he likely would have supported it as it aligns with his views. There's also a part of Gödel's philosophy about how math truth links to language or symbols. Some philosophers believe math truth is tied to formal systems or languages. What's true in one might not be true in another. This stems from non-standard models in logic and set theory results. Gödel rejected this relativism outright. He clearly separated math truth from the act of proving things in formal systems. Truth is fixed and unchanging. Proving things depends on the systems used. Just because these systems differ in strength doesn't mean truth is flexible. It simply means different systems highlight different parts of math reality. Likewise, having non-standard models doesn't challenge objectivity. When we put arithmetic into formal terms, the system includes numerous models, even strange ones involving infinite numbers. But this doesn't mean there isn't a true model of natural numbers. We create axioms to describe standard natural numbers, and that intention defines our focus, even if the system can allow alternative views. This ties into one of Gödel's key ideas. The meaning cannot be fully captured by formal systems. The essence of math concepts goes beyond any one set of axioms. We grasp the idea of a natural number through intuition, anchoring a specific structure as our intended meaning, even if formal systems can't fully capture it. That's why informal math reasoning is crucial. Simply playing with symbols can't replace true understanding. Finally, why does this debate between Platonism and other viewpoints matter? Why care if math objects exist independently or are merely human concepts? Does it affect anything practical? To Gödel, it was very important. If Platonism isn't true, math would lose its claim to objective truth and turn into just a consistent symbol game. Without objective math truth, the importance of incompleteness doesn't hold up. It would just show that various formal systems have different capabilities. The gap between truth and what can be proved would disappear, since there's no truth beyond proofs. Additionally, without Platonism, Gödel believed we couldn't truly comprehend how math advances. Why do mathematicians keep tweaking axiom systems, tackling unsolved problems, and clarifying ideas? Without a real puzzle to work out, their efforts might seem pointless. Platonism offers an explanation. Mathematical advancements mean uncovering details of a real, objective world. It's about improving how we describe mathematical reality. In the absence of Platonism, progress would just mean shifting between arbitrary rule sets. Platonism matters because of Gödel's broader philosophical views. His belief in reason, his optimistic view of human knowledge, and his thoughts on God rely on the existence of an actual realm of abstract truths that reason can access. If Platonism isn't correct, much of what Gödel believed would collapse. That's why Gödel devoted a lot of energy to defending his perspective on mathematical reality. Yet, despite all his arguments, he never claimed to provide undeniable proof of Platonism. He regarded it as one philosophical stance among others, but he thought it was the most reasonable. His work in logic and math was meant to back Platonism indirectly by showing its implications and the weaknesses of other views. Whether he succeeded or not remains a topic for debate, but his thoughtful defense of mathematical realism stands out as one of the most significant contributions to the philosophy of mathematics in the 20th century. Part 3. Back in 1938, just 7 years after Kurt Gödel's incompleteness theorems shook up the logic world, he made another groundbreaking discovery in math. He imagined a mathematical universe, a model of set theory, where the continuum hypothesis held true. Nowadays, we refer to this as the constructible universe, or Gödel's work wasn't just a technical milestone. It also made a philosophical point about mathematical reality and how we explore it. To understand what Gödel did and why it matters, we need to get familiar with set theory, the continuum hypothesis, and why solving it became a mission for mathematicians. This journey leads us into the mind-boggling world of mathematical infinity. Set theory kicked off in the late 1800s. Thanks to Georg Cantor's groundbreaking ideas, he showed that not all infinities are created equal. They actually come in various sizes. Consider the set of natural numbers, 1, 2, 3, 4, and so on. It goes on infinitely. But the set of real numbers, all possible decimal expansions, including numbers like pi and the square root of 2, represents a bigger infinity. There are more real numbers than natural numbers, even though both extend infinitely. It sounds like a puzzle. How can one infinity be larger than another? Cantor's logic was brilliant. To compare the sizes of sets, try pairing them off one by one. If you can match each element of set A with a unique element of set B with no leftovers, then A and B are the same size. Cantor demonstrated that when it comes to real numbers, no list can capture them all. You'll always leave some out. This diagonal argument proves you can't pair all real numbers with natural numbers, meaning the set of real numbers possesses a larger kind of infinity. Cantor didn't stop there. He introduced a whole hierarchy of infinite sizes, known as cardinalities or cardinal numbers. The size of the natural numbers is called Aleph null. Real numbers belong to a different level of infinity. But how much bigger are they exactly? That's where the continuum hypothesis comes in. Cantor's hypothesis suggests there's no cardinality between Aleph null and the real number's size. It claims the real numbers represent the next level of infinity after natural numbers, with no intermediate sizes. In formal terms, the continuum hypothesis states that the size of the continuum equals Aleph 1, the cardinal number following Aleph null. You'd think this would be a straightforward question with a clear answer. There's either an intermediary size or not. Cantor spent years trying to prove it, but fell short. So did the mathematicians who came after him. David Hilbert even ranked the continuum hypothesis as the top puzzle on his famous list of 23 unsolved math problems from 1900. Then Gödel stepped in. In 1938, he showed that if the standard set theory axioms, known as the Zermelo-Fraenkel axioms, or ZF, are consistent, then you can't disprove the continuum hypothesis using them. He accomplished this by creating a specific model of set theory, the constructible universe L, where ZF is valid and the continuum hypothesis is true. If you could disprove the continuum hypothesis with ZF, it would be false in every model of ZF, including L. But because it's true in L, you can't disprove it. And there's more to the story. In 1963, Paul Cohen used a method called forcing to prove that you also can't prove the continuum hypothesis from ZF. He built models where ZF holds, but the continuum hypothesis doesn't apply. Together, Gödel's and Cohen's results show that the continuum hypothesis is independent of ZF. The fundamental axioms of set theory simply don't resolve whether the hypothesis is true or not. At this point, it might seem like a letdown. We still can't nail down the answer, but it revealed something fascinating about what math can and can't accomplish, and the limits of formal systems. The continuum hypothesis isn't just some weird, invented question meant to be undecidable. It's a fundamental question about the structure of infinity. Still, our most trusted foundational axioms leave it unaddressed. This was the first glaring example of a major math puzzle that standard axioms can't tackle. Now, let's dive into exactly what Gödel did when he created the universe L. The math world of the 20th century witnessed truly awe-inspiring developments, and set theory played a big part in that story. It all starts with the empty set, which is exactly what it sounds like, a set with nothing in it. From this point, we can create more complex sets by doing things like forming subsets, creating unions, or making power sets. An example of set theory is a collection of sets that follow the ZF axioms. Here's the twist. There isn't just one model, there are many. Although they all stick to the same rules, they might contain different sets. Gödel came up with the idea of crafting the simplest model possible, yet still sticking to the ZF rules. He formed sets step by step, starting with the empty set and adding only the sets that were defined by formulas from sets previously formed. The resulting universe, built only with definable sets, is known as the constructible universe. This constructible universe, called L, has some cool features. Initially, it squares up with the ZF axioms, so it's a recognized model of set theory. Additionally, it validates the axiom of choice, a rule often debated in math circles that helps you choose elements from countless sets all at once. Most importantly, it aligns with the continuum hypothesis. In L, there's no wiggle room for sizes between Aleph 0 and the size of real numbers. So, why is it that L jibes with the continuum hypothesis? Simply put, by focusing only on definable sets, the universe remains as lean as possible without breaking any rules. In this tiniest universe, there's just no space for any extra sizes to crop up. Real numbers in L have the size Aleph 1, since we haven't thrown in any extra sets to boost sizes below the continuum. Although Gödel's setup was technically brilliant, he was even more fascinated by the philosophical questions it posed. If the continuum hypothesis can float freely from ZF, what does that say about mathematical truth? Is there a clear-cut answer to the hypothesis, or is that beside the point? Gödel, a Platonist, believed the continuum hypothesis must be either truly right or wrong, even if ZF didn't settle it. He suspected there was an actual reality to the math universe about how many sizes exist between Aleph 0 and the continuum. Our current axioms just don't fill in the whole picture to solve this. You know what that implies? We need new axioms to better outline the structure we're trying to explicate. Gödel thought these new guidelines would emerge from fine-tuning our basic understanding of a set. So, what is a set exactly? It's a group put together by specific criteria. The ZF axioms cover some of this, but they aren't the full story. By diving deeper into what sets mean, we could discover new rules, axioms that seem obvious once you see them, but can't be drawn from the ones we know. This introduces large cardinals. These axioms suggest that there are some extremely large, infinite sets with special traits. They extend beyond ZF, claiming things like the existence of inaccessible cardinals, measurable cardinals, supercompact cardinals, and even more massive infinities. Gödel predicted the role of these large cardinals. Back in the 1940s, when they weren't much of a hot topic, he argued they'd be pivotal for set theory. He saw these axioms as offering key insights into the nature of sets, revealing the depth and breadth of the set hierarchy and the sorts of infinite structures it might support. More specifically, Gödel hoped these large cardinal axioms might unlock the continuum hypothesis. Perhaps, if we accepted axioms that promise really huge cardinals, we could figure out whether middle-sized sets exist. The true or false nature of the continuum hypothesis might depend on these stronger axioms that better define our concept of sets. So far, that dream hasn't come true entirely. Large cardinal axioms have proven immensely important in the field of set theory. They provide a set of foundational systems, each level surpassing the previous one. Many riddles unsolvable by ZF fall when large cardinal axioms are used. Plus, delving into these cardinals has brought to light deep connections across different areas of math. Even with lots of large cardinal axioms involved, the continuum hypothesis is still up in the air. Those axioms don't settle the matter. But Gödel kept pushing to uncover new axioms to tackle unsolved questions. Some mathematicians believe we'll eventually pinpoint the right axioms to settle the continuum hypothesis. Meanwhile, others think the question is inherently vague, with different set theory worlds providing different answers. This debate dives deep into math philosophy. Is there a single true mathematical universe, or are there many math realities just as valid? Gödel was sure there was only one mathematical universe. He thought sets fit into a specific structure, and there are definite answers to their sizes. The various models just highlight how our current axioms aren't detailed enough to capture this unique structure. Just like how better scientific theories describe the real world more accurately, better axioms will lead us to the true math universe. Let's look at Gödel's work on the axiom of choice, closely linked to his study of the continuum hypothesis and constructibility. The axiom of choice says you can select one thing from each set in any group of non-empty sets, even if it's infinite and lacks a way to choose. While it sounds simple, it has mind-bending consequences. It results in non-measurable sets, ones where you can't logically assign size or volume. It also brings about the Banach-Tarski paradox, which claims you can break apart a solid ball and reshape it into two identical ones. Physically, it seems impossible, but mathematically it checks out with the axiom of choice. Some mathematicians rejected it because of such weird outcomes, arguing it allowed random selections without any clear method. They thought math should stick to things we can specifically construct or define, not mysterious ones made by mere assertion. Gödel's constructible universe, L, provided an answer. He showed that if ZF is consistent, then adding the axiom of choice to it keeps it consistent too. Inside L, the axiom of choice naturally applies, proving its merit by demonstrating it doesn't cause contradictions. Accepting ZF leads you to accept the axiom of choice comfortably. Philosophically, Gödel's work suggested the axiom of choice reflects a basic feature of set structure. In the simplest universe satisfying ZF, choice holds true, making it seem like a natural rule, not a random one, even if its choices don't seem constructible. Gödel had mixed feelings about constructibility. Proving the axiom of choice and the continuum hypothesis were consistent was a big win, but he didn't see L as the final set theory universe. He believed the true universe of sets was way bigger than L. He went for maximality principles, thinking the set theory universe should be as vast as possible within logical bounds. Only allowing definable sets felt arbitrary and limiting. Why should the math world be limited by what we can define? Gödel felt the real universe should include any set that can reasonably exist beyond just definable ones. This idea was evident in his work. He got major results about L, but didn't back it as the ultimate set theory model. He saw L as useful for proving consistency, showing what's possible with ZF, but not the whole truth about sets. Gödel's drive for maximality was inspired by Leibniz, who thought God created the best possible world, the fullest universe consistent with logic. Gödel believed math should mirror this completeness. Limiting to constructible sets would cut short this richness, tying into his efforts to expand ZF through maximality principles. A maximality principle suggests that if you can think of a set without running into contradictions, then it really exists. If you can logically outline a collection, it's considered a set. The idea is to make the world of sets as big and varied as possible. Gödel had a theory that right maximality axioms might solve the continuum hypothesis. He even thought the hypothesis could be wrong. His view was that these principles should create a universe with various sizes of infinity between the smallest and the continuum, because not having in-between sizes seemed too restrictive. Though he didn't fully develop or publish this theory, it showed how he philosophized about axiom choice, aiming for ones that fit natural intuition about sets and clear up unanswered questions. He hoped to resolve the continuum hypothesis with meaningful axioms rather than arbitrary ones. Today's set theory has come up with various ways to expand ZF. Forcing axioms, an extension of Cohen's forcing method, have done well. Some axioms are tied to large cardinal theories or borrow from category or topos theory to propose other foundations, but none have fully answered the continuum hypothesis, which is unresolved. This lack of agreement might have frustrated Gödel, who wanted natural axioms that could solve big questions. Set theory has branched into different research areas, but no clear solution has emerged. Some think this shows a kind of pluralism, suggesting there isn't just one correct answer. Others believe we haven't found the right axioms yet. Switching topics, let's dive into another part of Gödel's work in logic that ties into set theory. His completeness theorem from 1929. Often mixed up with the incompleteness theorems, it's a separate idea with its own impact. The completeness theorem says that in first-order logic, every valid statement can be proven from standard logical rules. If a statement holds true in every view of logical symbols, it can be proven. This means the proof system can capture all logical truths, but not every truth in a specific subject entirely. Published before the incompleteness theorems, it's almost in contrast to them. Logic is complete because you can demonstrate all logical truths. However, arithmetic and set theory are incomplete, holding truths that can't be fully accounted for by standard axioms. This difference lies in their ability to express ideas. First-order logic is limited enough that its truths equal its provable statements. Arithmetic and set theory are richer, with truths extending beyond what you can prove. Gödel's completeness theorem had a massive effect on logic, bringing model theory and proof theory together. It showed that a statement is provable only if it's true in all situations, creating a foundation for modern logic. It also linked consistency with the existence of models. A theory is consistent if it has a model. But there's a philosophical puzzle here. Completeness means logic captures all truths. Everything valid can be proven. Yet incompleteness shows no axioms can encapsulate all of mathematics. How do these coexist? They show logic and mathematics have different natures. Logic looks at form, ignoring content. Any expression just using logical symbols like quantifiers and variables follows logical rules. Mathematics, on the other hand, involves substance through concepts like numbers, sets, and functions, adding a complexity beyond what logic alone solves. When you add math axioms to logic, you see incompleteness. Gödel saw this as a deep insight. Mathematical concepts can't be reduced only to logic. Concepts like numbers have aspects beyond purely logical representation. That's why math has its own rules, separate from those in logic, and why some mathematical truths might always be unprovable. This view aligns with Gödel's critique of Frege and Russell. They tried to reduce math to a branch of logic, claiming that mathematical truths are just complex logical ones. But Gödel's theorems on completeness and incompleteness poked holes in that idea. Logic is complete, while mathematics isn't, meaning not everything in math can be expressed in logical terms. Math stands apart with its own unique subject. Gödel explored practical uses of the completeness theorem. It leads to the compactness theorem, which says if every finite subset of axioms has a model, then so does the whole infinite set. This results in models that match the axioms but differ from what we expect. In arithmetic, compactness means there are models with infinite numbers going beyond the usual natural numbers. These unusual models follow the arithmetic rules, but contain quirky elements. In set theory, models might show different sizes and levels of infinity. They follow the axioms, but vary a lot in how they're structured. Does this hint that arithmetic and set theory have no single true interpretation? Some philosophers think so. The axioms don't perfectly define the subject, so there's no real answer to which model is correct. They believe mathematical truth relies on the chosen model. Gödel was against this idea. He argued that our aim is to discuss the standard natural numbers or the entire universe of sets. Even if our axioms don't perfectly capture this aim, it's there. Non-standard models highlight the limits of first-order logic rather than challenge the notion of objective mathematical truth. This links to his Platonism, where mathematical ideas are clearly understood, implying a single true interpretation even when axioms fall short. We adjust axioms when they fail to match our intentions, but the concepts themselves remain objective. Wrapping this up, let's think about Gödel's impact on set theory. His work on constructibility, the continuum hypothesis, and large cardinals reshaped the field. The methods he started, like inner models, consistency proofs, and relative consistency, are now common. His belief in finding new axioms to solve unanswered questions drives current research. Yet, the problems he cared about still lack solutions. The continuum hypothesis remains unsolved even with big cardinal axioms, and there's no consensus on which axioms should extend ZF. Debates on what mathematical truth means and the nature of sets continue. Some may see this as a failure, thinking Gödel's goals weren't met. Others see it as proof of the complexity and challenge of his questions. Post-Gödel, set theory has evolved into a complex field, exploring the vastness of infinity and the roots of mathematics. His theorems on incompleteness and constructibility showed that simple answers are out of reach, leading mathematicians to create new ideas and methods. Ultimately, perhaps the biggest lesson is that math has no boundaries. No matter how much we stretch our axioms, independent questions will always be there. The structure of mathematical reality is so rich that no finite set of axioms can completely describe it. This isn't a flaw, but a testament to math's endless depth. Gödel highlighted this richness, and his work remains essential for anyone exploring the true nature of mathematical truth. Part 4. A deep dive into logic's completeness. Before flipping mathematics on its head with his incompleteness theory, Gödel made another monumental find: the completeness of first-order logic. He nailed down this groundbreaking concept while working on his PhD in 1929 when he was just 23. His completeness theorem showed that in first-order logic, anything that holds true logically can be proven formally. So, at least in this realm, things line up perfectly. This feat alone would have cemented Gödel's legacy in logical history. But the techniques he developed for this theorem were what eventually led to his more famous work on incompleteness. Understanding what he discovered its significance, and how it ties into his later work gives a glimpse into the unified nature of his pursuits in logic. The challenge Gödel faced revolved around the relationship between meaning and truth, semantics, and formal proofs, syntax, in logic. Semantics explores when a logic formula is true, while syntax investigates when it can be derived from axioms using logical rules. In 1928, Hilbert and Ackermann put forth a set of axioms and rules for first-order logic, questioning whether it was complete. Could every logically valid formula be formally proven? First-order logic incorporates quantifiers and predicates, allowing us to express ideas like, for all x, if x is human, then x is mortal, or there exists an x such that x is prime and x is greater than 2. These statements make use of quantifiers, like for all and there exists, related to objects described by predicates. A formula is logically valid if it's true regardless of interpretation. Consider a formula is proven when you can derive it using logical axioms and rules. Start with basic logical truths such as A implies A, and apply rules like modus ponens. If you know A and that A implies B, you can conclude B. The big question completeness addresses is whether these concepts, validity and provability, align. Gödel answered with a resounding yes. He confirmed that in Hilbert and Ackermann's first-order logic system, you could prove every logically valid formula. His smart proof showed that if a formula can't be proven, you can interpret it in a way that makes it false, meaning if it's not provable, it's not valid either. Thus, provability and validity are in sync. Gödel's approach sparked the field of model theory, demonstrating how you could construct models to systematically verify formula truth. His ideas brought a sharp focus on the interaction between syntax and semantics in 20th century logic, driven largely by Gödel's completeness theorem. But why is completeness such a big deal? What does it mean if valid formulas can be proven? First, completeness reassures us that formal proof systems encompass all logical truths. Wondering if something's logically valid? Prove it. If it's valid, a proof exists somewhere. It means logical reasoning can be entirely formalized without leaving anything out. Second, completeness ties consistency to satisfiability. If a set of axioms doesn't lead to contradictions, there's a model where they're all true. Finding a model is a powerful method to demonstrate consistency. Third, completeness introduces the compactness theorem, which says if every finite part of an infinite set of axioms has a model, so does the entire set. This is invaluable for building unusual structures and showing certain things exist in math. Lastly, and importantly for philosophy, completeness shows both the strength and limitations of first-order logic, allowing us to reformulate almost all of mathematics within its framework. It's comprehensive, meaning it delivers a strong impact without becoming indecipherable or lacking elements. This makes it different from second-order logic, which doesn't just focus on individuals, but also lets you quantify over properties and sets. For example, you can say that if a property P holds for 0 and maintains its truth through its forms, then it's true for all natural numbers. That's how second-order logic expresses induction. While it's more expressive than first-order logic, there's a downside. It's not complete. Some statements in second-order logic can't be fully proven, and there's no definitive way to list all such statements. Gödel observed this contrast. First-order logic strikes a balance between expressiveness and practicality. It's just weak enough to ensure that truth aligns with proof, yet strong enough to cover most mathematics without perfectly isolating structures like the natural numbers. In first-order arithmetic, you come across non-standard models containing infinite numbers. Stepping into second-order logic, you gain a unique grasp of the standard model, but lose completeness along the way. This reveals something about mathematical concepts. Truly understanding them requires more than first-order logic, but venturing into higher orders presents a trade-off. You either achieve completeness or a categorical perspective, but not both. Gödel believed mathematical concepts are richer than any one logical system can fully capture. Consider natural numbers. They point to a unique structure, the standard natural numbers, but no set of first-order rules can define it uniquely. You need second-order rules for that, which leads to losing completeness. It shows that grasping math requires intuition beyond formal logic, a feel for concepts that inform interpretation. Now, let's shift focus to another part of Gödel's contributions in logic, his dialectica interpretation of arithmetic. Released in 1958, it delved into arithmetic's foundations through a proof-centric approach. This was Gödel's way of engaging with Hilbert's program and intuitionism, even though he didn't fully align with either. Hilbert's program sought to demonstrate the consistency of mathematics using reliable, constructive methods. The aim was to view math as a formal system and mathematically prove the system's non-contradiction. This proof needed to utilize methods that even those wary of infinity would accept: finite, practical reasoning with clear symbols. Gödel's second incompleteness theorem disrupted these plans. Arithmetic can't prove its own consistency with its internal tools. To establish arithmetic's consistency, something more robust is required outside of arithmetic. This appeared to spell the end for Hilbert's program, but another aspect involved reworking classical math into intuitionistic or constructive math. Intuitionism, led by L.E.J. Brouwer, rejects the law of excluded middle and other classic logic principles, adhering to constructive proofs. This means you need to build something to prove its existence and prove either A or B by directly proving one. Classical logic is more flexible, permitting indirect proofs and non-constructive arguments. Gödel explored whether classical arithmetic could be integrated into intuitionistic arithmetic. Could classical proofs be converted into constructive ones, showing that if something's provable classically, it's also provable constructively? This would act as another form of consistency check. If intuitionistic arithmetic is reliable, so is classical arithmetic. The dialectica interpretation achieved this artfully. Gödel showed how to translate classical arithmetic into a system called T, a constructive system with primitive recursive functionals. Every classical arithmetic theorem had its counterpart in system T. This proved classical arithmetic's consistency relative to system T, despite system T being quite powerful itself, stronger in some ways than intuitionistic arithmetic. So, this doesn't entirely suggest classical methods are additions to constructive ones. Instead, it highlights the extra assumptions needed for classical reasoning. Philosophically, Gödel wasn't wholly convinced by intuitionism, finding constructivism somewhat restrictive. Math isn't just about what we can tangibly construct. Classic mathematicians have the luxury of stating the existence of certain things even if they can't directly build them, as this mirrors the truth of the mathematical universe. We can prove some structures exist even if we can't craft them with our own hands. Yet, Gödel had a lot of respect for intuitionism, seeing it as a valid viewpoint worth diving into. His dialectica interpretation was a part of this journey, illustrating the deep connection between classical and intuitionistic arithmetic, despite their differing mathematical foundations. Gödel also explored intuitionistic logic. Back in 1932, he proved that intuitionistic propositional logic can't be captured with merely a finite number of values, which shot down earlier attempts to simplify its semantics using a fixed number of truth values. Intuitionistic logic, if it has any truth-value system, demands infinite values or something more intricate. This burst into what we now call Gödel-Dummett logic, which bridges intuitionistic and classical logic. It's not as strong as classical logic, but more robust than intuitionistic logic. While Gödel didn't go deep into developing this system, it's vital today for the study of diverse logical frameworks. A philosophical question popping out from these explorations is about the essence of logic itself. Is there a single true logic, or are there multiple valid systems, each serving its unique purpose? Classical logic embraces the law of excluded middle, asserting every statement is either true or false. However, intuitionistic logic denies this, especially concerning infinity or non-constructive existence. So, which one has it right? Gödel was convinced that classical logic is accurate for reasoning about objective mathematical reality. Consider the continuum hypothesis. It's either true or false, even if we haven't discovered which yet. Intuitionistic logic centers on what's known or constructible, rather than what exists in reality. It's handy for certain foundational studies, but doesn't completely cover mathematical truth. This perspective stirs up controversy. Some argue that logic should center on inference patterns more than metaphysical declarations. Different kinds of logic fulfill various roles, hinting that no single logic is the absolute truth. Gödel would likely beg to differ, arguing logic aligns with objective truth, with classical logic hitting the mark for mathematics. Let's explore another one of Gödel's insights: proof theory and ordinal analysis. Proof theory looks at proofs as mathematical objects with structures. Ordinal analysis ties ordinals to formal theories to measure their proof-theoretic strength. While Gödel wasn't as deep into proof theory as model theory, he did engage with it within the framework of Hilbert's program. In 1936, Gensen showcased arithmetic's consistency using transfinite induction up to ordinal epsilon, after Gödel's incompleteness theorem showed arithmetic's inability to prove its own consistency. Although Gensen's methods transcended arithmetic's formal capacity, like transfinite induction, this couldn't negate incompleteness. Gödel noticed stronger proof-theoretic techniques could cement the consistency of weaker systems. This suggested a hierarchy of proof-theoretic strength, each layer proving the consistency of those below, crucial to current proof theory. The takeaway here is that mathematical knowledge is structured. We don't need universal foundations that prove their own consistency. Instead, we validate weaker systems using stronger ones in a chain. As long as this progression goes upwards and avoids going in circles, as incompleteness ensures, circular reasoning is sidestepped. Gödel also saw that proof-theoretic strength doesn't have to parallel set-theoretic strength. A theory might be weak in one area but robust in another, capturing different domains of power. This pluralistic view of strength reflects Gödel's sophisticated understanding of mathematical foundations. Now, let's see how the completeness theorem and incompleteness theorems tie into Gödel's broader vision for logic and mathematics. At first glance, these ideas seem to clash. The completeness theorem claims that logic can handle all valid reasoning, but the incompleteness theorem says arithmetic contains truths that go beyond what axioms can prove. So, how can both be right? The thing is, logic and math aren't identical. In its simplest form, logic deals with basic logical concepts and is complete, but math ventures into bigger ideas like numbers and sets, going beyond pure logic. When you add math axioms to the mix, that's when incompleteness crops up. This indicates math can't just be reduced to logic. Freya and Russell attempted to prove arithmetic was basically disguised logic, suggesting math truths were simply logic truths. Yet Gödel's theorems proved them wrong. Logic is indeed complete, but arithmetic doesn't measure up. That's why arithmetic isn't pure logic. Math addresses topics that logic alone can't cover. From Gödel's Platonist view, this all makes sense. Math concepts aim to describe objective structures. Whether we're talking about natural or real numbers or the set universe, these structures have aspects that no formal system can completely capture. Logic serves as a reasoning tool, but math requires an intuitive grasp of its unique ideas. The completeness and incompleteness theorems reveal something crucial about proof. In the realm of logic, proof means formal deductions from axioms, complete in pure logic, but not in math. An intuitive proof, persuasive reasoning that establishes truth, extends beyond just formal deduction. Recognizing a Gödel sentence as true involves using an informal proof that goes beyond formal rules. Gödel believed this informal aspect is always present in math. We can't dismiss essential understanding for the sake of fully automated reasoning. Developing things formally aids clarity and consistency, but doesn't replace mathematical insight. That's why creativity in math matters. Discovering new theorems means recognizing patterns and connections that formal methods alone won't uncover. Some philosophers and computer scientists resist this idea, aiming to fully automate math by turning proof into algorithms. Automated theorem provers have indeed done amazing things, even proving complex theorems. But they work within fixed frameworks without the ability to create new axioms or notice gaps in a system. They lack the intuitive insight human mathematicians bring. Gödel probably foresaw this limitation. Intuition can't be fully replicated by algorithms because it involves understanding beyond rigid rules. This doesn't mean intuition is mystical or supernatural. Rather, it's the mental skill to grasp conceptual connections, not just following set procedures. In wrapping up this section, we should reflect on Gödel's broader impact on logic. Before his work, logic was mainly about philosophy, dissecting arguments, and refining reasoning. After Gödel, logic took a more mathematical path, rigorously studying formal systems with mathematical tools, thanks to him. The completeness theorem laid the groundwork for model theory. Incompleteness theorems opened up metamathematics and the study of formal systems as mathematical objects. Techniques Gödel introduced, like arithmetization, Gödel numbering, diagonal arguments, and inner models, have become crucial tools. Modern logic without these is hard to imagine. Gödel also highlighted how intricately logic and math are connected. Insights in logic impact math, and math results have logical significance, blurring the boundaries between logic foundations and math. This interdisciplinary nature defines today's logic and foundational studies. Yet, Gödel never shied away from the philosophical side of logic. Unlike many modern logicians, he genuinely contemplated what logical discoveries meant for math, truth, and knowledge. To him, the completeness theorem wasn't just a technical achievement, but a demonstration of formal reasoning's power. The incompleteness theorems weren't just limitations of formal systems, but offered insight into the nature of mathematical truth. This blend of technical skill and philosophical understanding made Gödel unique in his field. He used math to explore philosophical questions and let philosophical insights guide his mathematical work. His work in logic proves that blending technical know-how with deep thought can really illuminate things. Understanding logic involves more than just nailing the technical side. It's also about having a philosophical feel for it, something Gödel managed throughout his career. Part 5. Physics, Relativity, and Cosmology. In 1942, Kurt Gödel sat in on a bunch of cosmology talks at the Institute for Advanced Study in Princeton. That's where he bumped into Albert Einstein. They became fast friends, taking daily walks and having deep conversations about physics, philosophy, and math. This friendship between a top-tier logician and one of the greatest physicists of the century led to a brilliant intellectual partnership. Gödel got super interested in Einstein's general relativity during the mid-40s. By 1949, he made an incredible discovery, a precise solution to Einstein's field equations that showed a rotating universe. Remarkably, this universe included closed time-like curves, basically paths through space-time that loop back on themselves. In Gödel's universe, traveling back in time wasn't just science fiction, it was rooted in real mathematical applications of Einstein's theory on gravity and the nature of space-time. Gödel demonstrated that while general relativity describes our current universe, it also allows for scenarios where causality doesn't make sense and time loops around. This revelation astonished Einstein and continues to influence discussions in physics and philosophy. Let's simplify what Gödel discovered and why it's important. To start, Einstein's theory of general relativity changed how we view space, time, and gravity. According to this theory, space-time isn't just a static background for events, it's dynamic, bending in the presence of matter and energy. The gravity we experience results from the bending of space-time around heavy objects. The Einstein field equations connect the bending of space-time with the distribution of matter and energy. Given a particular matter setup, these equations determine how space-time should curve. Conversely, understanding the geometry imposes constraints on possible matter setups. A solution to these equations gives a specific geometry and matter distribution that meets the criteria. For example, the Schwarzschild solution explains space-time around a spherical mass, like a star. The Friedman-Lemaitre-Robertson-Walker solutions relate to expanding or contracting universes, forming the backbone of modern cosmology. Each solution represents a possible universe as per general relativity. Gödel introduced a new one, a rotating universe filled with perfect fluid dust, symbolizing simplified galaxies. Instead of expanding, this universe spins. The geometry of this universe is captivating. It's homogeneous, meaning each point looks the same as others, and it rotates around a specific axis. From any viewpoint, an observer would see the universe spinning around them without a central pivot. The details involve defining the metric, a way to measure distance and time in space-time, so it fulfills Einstein's equations for an acceptable matter structure. Gödel's metric is both graceful and symmetrical, rich in its mathematical depth. But the exciting part is what it means physically. Gödel's universe has closed time-like curves. This means someone could travel through space-time and end up back at their starting point in both space and time. You could jump into a spaceship, set off in a certain direction, spend a long time traveling, and come back to your starting place before you even left, meeting a younger version of yourself. How does that work? In general relativity, the geometry of space-time dictates which paths are time-like, paths people can travel at slower than light speeds. Typically, all time-like paths extend infinitely in both directions. But in Gödel's rotating universe, the combination of spinning and curvature of space-time makes these paths loop. Imagine space-time as a twistable fabric. In a flat scenario, no trip gets you back to your past. But Gödel's spin bends space-time so much that what starts as a forward path eventually circles back. Walking a straight line through this twisted cosmos brings you right back to where you began. This concept shocked Einstein. He was used to the relativity of time, but always thought causality was unbreakable. Things usually follow a set sequence, with causes coming before effects. But when closed time-like curves come into play, this idea gets flipped on its head. Imagine being able to travel back to your own past. Suddenly, you could face bizarre paradoxes. You might prevent your own birth, eliminate your grandfather before your parent is even a thought, or just land yourself in a tangled web of logical issues. Gödel was aware of these paradoxes, but they didn't bother him. For him, closed time-like curves hinted that time might not be the straightforward thing we think it is. Our usual concept of time, flowing from past to future, doesn't quite fit with how space-time is actually set up. Gödel believed time was more like a mental construct than a real aspect of the universe, reflecting his interest in Kantian and idealist philosophies. We'll touch more on that later, but his main point wasn't just about time travel having paradoxes. He was suggesting that if we have closed time-like curves in solutions to Einstein's equations, maybe the common idea of time isn't physically real. He argued that if Einstein's equations let universes exist with these curves, and those equations truly describe space-time, then it must tell us something about time's nature everywhere, including in our universe. This implies there's no real global time, no way to keep events in a consistent order for everyone. Normally, you can set up a global timeline that organizes events neatly. But in a universe like Gödel's, that's impossible, hinting at a more flexible and chaotic concept of time than we're used to. Critics were quick to respond, pointing out that our universe doesn't spin like Gödel envisioned. Observations don't show massive cosmic rotations, making his idea seem more like a clever math trick than an actual description of reality. Gödel expected this criticism. He wasn't claiming our universe matched his model exactly. Rather, he was showing that the physical laws we follow, like Einstein's equations, allow for such universes. This fact reveals something about the laws, and thus about all possible universes under them. It's like imagining frictionless machines or perfect collisions with Newton's laws. These aren't real, but they help us understand the mechanics better. Similarly, examining Gödel's rotating universe offers insights into general relativity and how it handles time in any universe where it applies. What Gödel thought he revealed was that general relativity doesn't inherently support the idea of time as a flowing entity. The theory describes space-time, but doesn't single out any particular version of past, present, and future. In essence, time in this view isn't at the core of reality. It's a perception we have while moving through space-time. This remains a debated topic. Not everyone agrees with Gödel's conclusions. Some physicists and philosophers argue that he stretched the idea a bit too far. Just because a theory has unusual solutions doesn't mean they apply to reality. General relativity also entertains things like wormholes and naked singularities, but that doesn't necessarily mean they're part of our universe. Plus, newer studies show not all rotating universes need closed time-like curves. Some can spin without enabling time travel, which weakens Gödel's argument that rotation plus general relativity equals time being a conceptual thing rather than a physical fact. Nevertheless, Gödel's ideas sparked a huge interest in the causal structure of space-time. Scientists started digging into which space-time setups allow for such time loops, when they could exist, and if we might create them ourselves. This led to ideas like chronology protection, hypothetical ways to prevent closed time-like curves from forming. Stephen Hawking even suggested a chronology protection conjecture, proposing that the laws of physics might outright prevent any time traveling to the past. Whenever circumstances allow for closed time-like curves, quantum effects seem to step in and halt them. This idea hasn't been proven yet, and there's a good number of doubters among physicists. The whole debate got started because Gödel discovered that classical general relativity permits time travel. Gödel's work also taught us that the big-picture structure of space-time is super important. Back in the day, relativity was all about local elements like point curvature and particle paths. But Gödel showed that global topology, the way space-time loops overall, is what really carries weight. This insight became central in modern cosmology and the study of black holes. Now, let's get into Gödel's universe details. The space-time he described is homogeneous, meaning it looks the same no matter where you go. There's no special area, yet it's not the same in every direction. The universe's rotation messes with the symmetry, and every observer notices an axis around which everything spins. The universe's material is a perfect dust-like fluid with uniform density throughout. This idealized dust reflects zero-pressure galaxies. The fluid spins at a speed tied to density via Einstein's equations. The balance between rotation and gravity keeps the universe stable, neither growing nor contracting. Gödel found a specific mathematical format for space-time metrics, incorporating hyperbolic functions with a cylindrical symmetry around the spin axis. Geodesic calculations, which are essentially the natural paths free-falling observers follow, reveal the closed time-like curves, which involve lengthy journeys rather than simple loops. And there's more. light behaves oddly in Gödel's universe. If you shine a light from a point, it spreads out, but eventually comes back together later along the rotation axis, thanks to the combined effects of rotation and curvature, a focusing phenomenon that's unlike most other cosmologies. Gödel even considered if his universe, with a few adjustments, could become a real cosmological model. A rotating yet expanding universe might fit observations while keeping its unique features. But challenges arose. Rotation strong enough to create closed curves conflicts with the observed isotropy of the cosmic microwave background on large scales. Today's cosmology imposes strict limitations on possible universe rotation, indicating it's too slow to form closed time-like curves. Thus, Gödel's exact solution doesn't align with reality, but the questions it raises are still important. One issue reminds us of the connection between math and physics. General relativity deals with math concepts through differential geometry, predicting with equations. These equations yield a variety of solutions, many of which don't fit physical reality. Which solutions describe potential universes? Which are just math curiosities? Gödel's universe fits seamlessly into Einstein's equations. It's no approximation or edge case. Mathematically, it stands on par with the Friedman-Robertson-Walker models that describe our universe. Yet, from a physical angle, it seems bizarre. What's the basis for sorting physically realistic solutions from the far-fetched ones? One idea involves initial and boundary conditions. Our universe began with the Big Bang and specific initial conditions, thus limiting relevant solutions to those that fit. Gödel's universe can't be ours because it's static and spinning, rather than expanding and isotropic. Still, Gödel might argue otherwise, claiming that if any space-time form fits Einstein's equations, it's a physical possibility in some manner. These equations are supposed to describe the laws of gravity and the nature of space-time. If closed time-like curves align with these laws, they suggest deeper space-time insights, even if our universe lacks them. Here's how that argument goes. Special relativity turned our understanding of time on its head, showing that simultaneity isn't something everyone can agree on. Two events might seem to happen at the same moment for one observer, while for someone moving relative to them, those same events might occur at different times. There's no clear-cut answer about distant events happening at once, flipping the idea of a universal present day upside down. Then, general relativity comes along and makes things even more complicated. Describing simultaneity in curved space-time just adds layers of confusion. In some setups like our expanding universe, we can still sort events with a kind of universal time. But this order isn't a one-size-fits-all. It heavily depends on how you break down space-time into spatial layers, and it's far from a universally recognized now. Gödel's idea about a spinning universe really takes this further. In a scenario with closed time-like paths, you can't forge a consistent global timeline. It's impossible to assign time to events in a way where time simply marches forward without running into contradictions. Events might actually end up being earlier and later than themselves. Gödel believed this shows that our natural idea of time as flowing from past to future isn't part of space-time's fundamental structure. Space-time is governed by geometric characteristics described using a metric tensor and curvature, as well as causal relations dictating event influence. However, it doesn't inherently include a present moment or direction for the flow of time. If time had intrinsic reality, Gödel suggested, Einstein's equations wouldn't allow for universes without it. The fact these equations allow for timeless universes suggests time isn't built into the laws of general relativity. And since these laws accurately capture space-time's essence, time doesn't count as part of objective physical reality. Critics jumped in, noting our universe isn't timeless. It expands, not rotates, featuring a distinct cosmic time. So, Gödel's perspective only argues that time isn't necessary within general relativity's framework. Not that it doesn't exist in our universe. But Gödel countered, despite not swaying everyone. He said the mere potential for timeless universes under the same laws as ours implies time isn't a core reality feature. If time were an absolute aspect, it'd have to exist in every universe described by general relativity. Finding a single universe without time proves it's not required by the laws themselves. Imagine a theory allowing three-dimensional and four-dimensional universes. This would suggest the number of spatial dimensions isn't set by fundamental laws, but by specific setting conditions. Similarly, if general relativity can support both time-bearing and timeless universes, the temporal structure isn't basic. Whether this claim holds up is arguable. Many philosophers don't agree that just because some universes lack time, it means time isn't objectively real in any universe. They claim time might still be real where it's present, even if absent elsewhere. Different solutions to Einstein's equations could portray different philosophical traits. But Gödel touched on a deeper notion. The essence of physical laws indicates what's fundamentally real. Features of specific solutions don't define the core of physical reality. Only traits found across all solutions or embedded in the laws themselves are considered true. Since time doesn't fit this, it's seen more as an ideal concept. This viewpoint aligns with Gödel's rationalism. He believed logic reveals reality's true nature by examining physical laws and mathematical structures. Empirical work uncovers these laws, but rational analysis digs into what truly exists. Since time appears in some solutions but not others, it's not deemed fundamental. Exploring further into Gödel's thoughts brings us to his connection with Kant. Kant became the first philosopher Gödel studied deeply, starting with the Critique of Pure Reason in his teen years. Throughout life, Gödel both respected Kant and found fault with what he saw as Kant's errors. Gödel's complex feelings about Kant reveal a lot about the development of his own philosophy. Kant had this idea of separating phenomena, what we perceive, from noumena, which are things as they actually are. He suggested that time and space are part of phenomena, meaning they are how we perceive the world rather than attributes of the world itself. Known as transcendental idealism, this perspective avoids denying the reality of the external world altogether. It doesn't suggest the world isn't real, just that we can't grasp it in its true form. We understand it only through our senses and the way we process information. Gödel appreciated this viewpoint, seeing Kant as someone who acknowledged an independent reality while understanding the role of the mind in shaping knowledge. However, Gödel felt Kant went too far in dividing phenomena and noumena. Kant believed the things themselves were unknowable, but Gödel thought reasoning could penetrate appearances and get a better hold on reality, particularly through mathematics and science. On the subject of time, Gödel agreed with Kant that our usual experience of time isn't the real picture. The now we perceive is just part of the phenomenon. But Gödel didn't think time was solely a mental construct. He believed that, in physics, time is objective, even if it doesn't align with how we feel it passing. Gödel eventually split time into two concepts: intuitive time, which involves our sense of past, present, and future, and physical time, which is about coordinates and a four-dimensional reality from relativity theory. Gödel maintained that the time we feel, intuitive time, happens in our minds, while the space-time described by physics actually exists. Physical time lacks the features we often associate with time, like moving from past to present to future. For human experience, time is more of an idea, even though space-time is real. This might seem confusing. How can he be a realist about space-time and an idealist about time? The answer is that space-time has a geometric and causal structure, but not in the intuitive way we think of time. We overlay our own timing sense onto occurrences in space-time to navigate our world, but this doesn't reflect how the world truly is. Gödel found inspiration in Leibniz, another influential thinker. Leibniz argued that space and time were about relationships between things, not entities themselves, echoing ideas from Einstein's relativity. However, Gödel also acknowledged the differences. Leibniz was an idealist about both space and time, while Gödel believed space-time was objectively real. Nonetheless, he felt a connection to Leibniz's mix of rationalism and metaphysics. Leibniz saw the world as fundamentally made of simple substances called monads, from which everything springs, aligning with Gödel's inclination to explore the deeper truths of existence. Gödel delved into Leibniz's less celebrated writings, believing there might be unnoticed insights purposefully ignored by others. He thought that perhaps there was an intention to suppress Leibniz's philosophical insights. This curiosity fueled Gödel's metaphysical reflections, even though he didn't develop a comprehensive system like Leibniz. His thoughts on time were also shaped by concepts from Edmund Husserl, the father of phenomenology. Exploring Husserl's ideas from 1959 onward had a profound effect on Gödel. Phenomenology digs into how we consciously experience various aspects of life, like our sensation of time passing. Husserl looked at how human consciousness links moments into a continuous flow, helping us make sense of sequence and duration. Gödel saw phenomenology as a structured way to refine concepts, especially concerning time. By exploring how we perceive time, we can distinguish subjective feelings from objective truths. This helps separate our intuitive understanding of time from physical time. While Husserl didn't endorse time being merely an ideal concept, as Gödel did, he focused more on comprehending our mental experience of time rather than arguing its reality or illusion. Gödel, however, believed Husserl's approach could validate the idea of time as a mental construct. By examining the essence of how we experience time, phenomenology shows that these elements are more connected to our consciousness than to the actual world. Gödel's idea about idealism is a bit intricate. He called himself an idealist, but still thought that both mathematics and physics had a reality of their own. How does that make sense? Well, it's about seeing different shades of idealism. Metaphysical idealism claims reality is all about thoughts or spirit. Like Berkeley famously argued that only minds and ideas were real. Gödel wasn't up for that approach. He thought reality stood by itself, consisting of abstract math and the real physical space-time. Then there's epistemological idealism, which suggests we can't truly know things directly, only through our own conceptual filters. Kant's take, transcendental idealism, falls along those lines too. Gödel didn't align with its stronger claims, thinking reason could uncover truths beyond just appearances. Still, he leaned towards a specific idealism related to our perceptions of reality. Time as a moving present? That's ideal. Expecting space to fit Euclidean patterns? Again, ideal. In truth, space isn't actually Euclidean. Absolute causality. Also ideal. These ideal angles derive from our experiences, not the world's true nature. So, Gödel shaped his own kind of idealism. He saw intuitive time as ideal, but recognized space as inherently non-real, balancing between an idealist view of perception and a realistic trust in abstract ideas and physical laws. This made him quite different from typical idealists, who generally idealized everything. Gödel's thoughts bring up a tricky philosophical issue about how we connect intuitive time and physical time. If our mental picture of time is off, why did we evolve to see it that way? Why would evolution give us minds that misinterpret time? Gödel didn't directly address this question, but maybe evolution designed our minds for managing the local space-time well. In our local environments, space-time might closely match our intuitive sense of time. Local happenings follow a clear order, with earlier causes leading to later effects. Hence, our intuitive sense of time works well for survival, even if it doesn't hold on a bigger scale, like in Gödel universes. This makes our intuitive idea of time similar to Euclidean geometry, reliable in local situations, but not on a grand scale. Our everyday environment seems Euclidean enough to handle routine tasks, but the larger universe shows non-Euclidean behavior. Additionally, there's a deeper question about our experience of time. Even if time as a flow is just an ideal, we still experience it passing by. It feels undeniably real. The philosophical discussion around this is vital. If time doesn't actually flow, why does it feel so real? Questions about how we perceive time remain open for philosophers and neuroscientists to explore. How does our brain create the sensation of time moving? Why do we have the impression of a present moment? How do we experience events unfolding or persisting over time? Gödel didn't have all the answers, but he stressed the importance of distinguishing between intuitive and physical time perceptions. Realizing that physical time doesn't fit our intuitive mold opens up avenues to explore how our minds create the experience of time's flow. Our experiences feel real even when they don't match objective time patterns. To wrap up, let's consider whether Gödel's idea of time as an ideal notion holds up. Scholars in physics and metaphysics continue to debate this. Those siding with Gödel think relativity theory redefines our understanding of time and reality. They view space-time as a fixed, four-dimensional block without true past, present, or future. It's all just our perspective. Gödel's idea of rotating universes suggests some spacetimes can't share a global time consensus. Critics, though, have other views. Some argue that relativity doesn't render objective time obsolete. Perhaps the present moment changes with different reference frames, yet remains objective within each. Or there might be a specific frame that governs absolute simultaneity, even if relativity doesn't specify it. Others point out that the theoretical notion of timeless universes doesn't mean our universe's time is just an ideal. What's truly real is what matters. Some folks acknowledge that physical time isn't exactly what we thought, but that doesn't mean it's all in our heads. Time is indeed real. It's just different than we imagined. Adjusting our idea of time to fit with the concept of relativistic space-time is a step forward, not evidence that time doesn't exist. I believe Gödel's argument points out significant issues, but it doesn't fully support the notion that time is just an idea. Instead, it shows that our gut feeling about time doesn't easily mesh with relativistic space-time, which rules out a flowing present and absolute simultaneity in fundamental physics. Whether this suggests time is just an abstract idea or that we're simply correcting our mistaken beliefs depends on how we define those ideas. What's undeniable is the influence Gödel's work had on discussions in the philosophy of physics. He showed that diving into precise solutions from Einstein's equations brings out conceptual and philosophical puzzles. He pointed out how mathematical physics and metaphysics can enhance each other and left us with a big philosophical puzzle. How do we align our perception of time with the structure of physical space-time? This question persists, highlighting the complex issues Gödel exposed by weaving logic, math, physics, and philosophy together in the search for time's true essence. Diving into Part 7, we're tackling the ontological argument for God. Back in 1970, Kurt Gödel was feeling the pressure of time ticking away. For years, he had quietly been working on a logical proof of God's existence, hidden away in his journals. With his end seemingly near, he allowed his colleague Dana Scott to make a copy of the proof, but only if Scott kept it secret. Gödel was concerned, as he later confided to his friend Oscar Morgenstern, that people might think he truly believed in God, even though he was just exploring a logical path. This comment was puzzling because Gödel genuinely did believe in God. He was known to read the Bible regularly, had his own theological musings, and often told friends he believed in an afterlife. So why keep a distance, or at least appear to do so? Perhaps he thought it would be strange for a logical thinker like him to present a proof of God's existence, or maybe the argument's abstract nature made it feel misleading to label it religious. Or, possibly, he knew there were flaws in the proof that he couldn't resolve. Gödel never published this ontological argument during his lifetime. It was only discovered posthumously in 1978, after his papers were sorted through and Scott's version was compared with Gödel's original notes. Since then, philosophers and logicians have analyzed it thoroughly, offering both critiques and defenses. Some computer scientists have even used automated theorem tools to verify its logical soundness. But does it genuinely prove anything about God? That's a topic of heated debate even now. To really grasp Gödel's proof, you've got to first understand the ontological tradition it stems from and the logical methods he used. Ontological arguments aim to demonstrate God's existence solely from the concept of God, using reason without needing outside evidence. This idea dates back to the 11th century thinker Anselm of Canterbury. Anselm posited that God, by definition, is the greatest being conceivable. If God only existed as an idea and not in reality, then something greater could be imagined, something with God's attributes plus actual existence. But that would contradict the concept of the greatest conceivable being. Thus, God must exist both in reality and in thought. Some critics found this reasoning too clever to be believable. How can you prove something's existence just by playing with concepts? Existence isn't an attribute like wisdom or strength that fits in a definition. Skeptics from Anselm's time, like Gonilo, up to Kant centuries later, dismissed ontological arguments as clever but flawed. Yet these arguments kept reappearing in new forms. Descartes argued that existence is part of God's essence, just like having three angles is essential for triangles. You can't think of God without thinking of existence, any more than you can think of a triangle with fewer than three angles. Leibniz expanded on this, saying the argument only works if God's existence is possible, meaning God's concept must be coherent. So Leibniz tried to prove God's existence is possible. This, combined with Descartes' idea, suggested God must exist. Gödel took Leibniz's approach and created his own proof. He used modal logic, which emphasizes necessity and possibility, and introduced the concept of positive properties instead of calling them perfections. The proof is complex, featuring axioms and definitions that lead to robust conclusions. Here's a simpler breakdown. Gödel starts with the concept of a positive property, without defining what makes a property positive, treating it as fundamental. Positive properties are those that enhance or perfect their subjects, like omniscience, omnipotence, and perfect goodness. Their opposites, ignorance, powerlessness, wickedness, are negative. Axiom 1 states that if a property is positive and requires another property to be true, then that property is also positive. Positivity is closed under necessary implication. If being all-knowing is positive and implies having knowledge, then having knowledge is also positive. Axiom 2 suggests that for any given property, either it or its opposite is positive, but not both. Every property is either positive or negative, with no in-between. Using these axioms, Gödel concludes in Theorem 1. If a property is positive, it might exist in something potentially. The proof is based on contradiction. Imagine that a positive trait couldn't exist. That would mean every trait, including negative ones, would be positive, which contradicts Axiom 2. So, positive traits have to be possible. Then Gödel explains what is meant by God. A godlike being has every positive trait, which is the first definition. God here isn't a creator, judge, or person, but simply the collection of all positive traits. According to Axiom 3, being godlike is itself a positive thing. This is a huge assumption, implying it's better to have every positive trait than only some. From Axiom 3 and Theorem 1, Gödel comes to Theorem 2. God could exist. It suggests the theoretical possibility of a godlike being's existence due to the positivity of being godlike, meaning these traits might actually exist. Up to this point, it only shows the possibility of God's existence, not a guarantee. The next part shifts from possibility to certainty. Gödel introduces essence. A trait is someone's essence if they have it, and it implies all other traits they possess. Essence includes everything crucial about something. He proves Theorem 3. If a being is godlike, godliness is its essence. This means God's nature is completely defined by all positive traits. Nothing about God is random beyond that. Then there's axiom 4. A positive trait is positive in every potential scenario. What's positive stays positive universally. Gödel explains necessary existence. Someone exists necessarily if every essence they have must be present. It means being in all possible worlds, not just our real one. Axiom 5 claims necessary existence is a positive trait, a controversial point, suggesting existing necessarily is better than existing by chance. A being that might not exist is seen as less perfect than one that must. From Axiom 5 and earlier results, Gödel shows Theory 4. God exists necessarily. This means being godlike is God's essence, and necessary existence is positive. Since God has all positive traits, God must exist in every potential universe, including ours. The argument stands if you accept the axioms and definitions. It's technically sound, even validated by computers. But does it actually prove God exists? Critics focus on the axioms. Why rely on axiom 2 that divides traits strictly into positive or negative with no neutral traits? Why believe axiom 5 that portrays necessary existence as positive? These aren't self-evident and demand justification, which Gödel didn't give. The biggest issue is modal collapse. Jordan Howard Soyle showed that Gödel's axioms imply if something is true, it's necessarily true. Nothing is contingent. Everything is predetermined. This conclusion is mostly rejected. If Gödel's axioms lead to modal collapse, they're flawed. Gödel knew problems might occur but didn't directly address the collapse issue. Some defenders tweak the axioms to avoid collapse while keeping the conclusion intact. Others argue the collapse isn't so bad, but most philosophers see it as the proof's downfall. Another criticism from people like Graham Oppy is that the axioms prove too much. If Gödel's logic works, it could just as easily prove the necessary existence of a completely evil being, a nearly godlike creature missing one trait or other oddities. The proof doesn't verify God's existence, but might highlight flawed axioms. There's also the question of what the proof actually establishes if it's valid. In Gödel's proof, the godlike being is just defined by having all positive traits, which seems quite removed from the traditional religious idea of God. Does this all-powerful being really care about people? Does it actually jump in to answer our prayers, perform miracles, or judge the living and the dead? Just having every amazing trait doesn't mean it would. Gödel's idea of a God might not be the usual personal deity, but something more like a force or an abstract ideal. He knew this, telling Morgenstern that his proof was about logic, not about pushing religion. Is this God anything like the one in Christianity, Judaism, or Islam? The jury's still out. At most, the proof hints that something with top-notch attributes has to exist. Deciding if this being is the same as a religious God takes more than just logic. So, why did Gödel get into this proof? It likely came from a few places. Curiosity, for starters. Ontological arguments are real brain teasers. Showing that solid modal logic could lay them out was an achievement in itself. Then, his love for reasoning. Gödel believed pure thought could reveal life's great truths. A solid ontological proof would back this belief. Lastly, his quiet interest in religion. Despite keeping it private, he had personal religious beliefs. A logical proof of God's existence would bolster these. Still, Gödel had his own doubts. Over many years, he adjusted the proof, suggesting he saw problems or limits. He never felt sure enough to publish it, hinting at his own uncertainty. His talk with Morgenstern also shows he was unsure how folks should interpret the proof. One view is that Gödel saw it as showing what follows from beliefs about perfection. If you agree that all perfections are positive, God has them all, and existing necessarily is a perfection, then God must exist. The proof lays out this if-then kind of reasoning. But whether the if bit is true needs philosophical debate beyond formal logic. For him, the ontological argument was more about clarifying concepts, not proving anything. It shows what one is committing to if they believe in a perfectly ideal being. It maps God's concept but isn't proof without accepting those starting assumptions. Jump to today, and philosophers have gone off in many directions with the ontological argument. Some are using modal logic to invent new versions by changing the axioms. Others are exploring what necessary existence even means through possible world semantics. Meanwhile, some dismiss ontological arguments entirely, agreeing with Kant that existence is not actually a property or perfection. Can we move from concepts to reality, or do claims that something exists always need real-world evidence? These questions span beyond just the ontological argument, hitting the core of philosophical exploration. Gödel's approach to the argument stands out for its logical intricacy and use of advanced higher-order modal logic. Whether it works as a proof or not, it shows how formal logic can tackle deep philosophical issues. It highlights the power of symbolic logic to create precise, testable points, but also marks its potential and limits in nailing down metaphysical truths using logic alone. There's something pretty intriguing, too. Gödel had this 14-point philosophical plan found among his notes. It spells out his major beliefs, lots of which tie into his work on this ontological proof. One point suggests there are other worlds with different sorts of rational beings. Another mentions that the world we're in now isn't the only one we've experienced or will experience. There's also a mention of a scientific, precise philosophy and theology that tackles super abstract ideas, which are really important for science. These hints suggest a view of reality that's much broader than just math and logic. Gödel thought there was a deeper reality beyond just the physical universe, packed with non-physical beings that could be understood through reasoning. His ontological proof was just a part of this bigger idea, with God being seen as the ultimate being in this complex metaphysical world that is known through rational thought. How exciting this concept seems really leans on one's philosophical perspective. Materialists and naturalists see it as unfounded speculation. People who believe in God or have idealistic views might find it intriguing, but they still might question if logic alone can back such significant claims. Gödel himself appeared torn between trusting the power of reason and recognizing its limitations. The ontological argument presents God as both incredibly ambitious and yet quite vulnerable. It's ambitious because it aims to prove the bold claim that God exists using just logic and definitions. But it's vulnerable because it rests on arguable assumptions and can lead to tricky outcomes. This acts as an illustration of rationalist ambition, showcasing both the strength and the risks involved in trying to understand reality through ideas. Part 8. Phenomenology and Gödel. At 53, back in 1959, Kurt Gödel experienced a major change in how he viewed philosophy. He got into Edmund Husserl's phenomenology and became convinced that it was the right way to approach philosophical questions. Husserl's ideas would go on to heavily influence Gödel's thoughts on mathematics, logic, and philosophical exploration over the next 20 years. This newfound passion for phenomenology was a significant turning point in his intellectual journey, although it often doesn't get the recognition it deserves. Phenomenology is all about digging into how we experience things and how our consciousness is organized. Husserl started it off in the early 20th century. This philosophy examines our perception of things, how we make sense of meanings, how we experience time, and how intentionality, our mind's focus on objects, helps us to understand the world. It aims to describe the core structures of experience through deep reflection and thoughtful analysis. So, what hooked Gödel on this approach? For a long time, he'd been wrestling with justifying mathematical Platonism, explaining how we know about abstract objects, and coming up with a solid philosophical approach. Phenomenology seemed like the solution. It offered a way to clear up concepts by looking at how our consciousness deals with them, recognized intuition as a real source of knowledge, and sought to be a rigorous science, Husserl's own phrase, far from speculative metaphysics. Gödel considered phenomenology as the only philosophy that truly respected Kant's main ideas. Husserl had deeply studied Kant with the aim of advancing his thoughts. Kant had suggested that we can't know things in their true essence, only in the way they appear to us, through our perception and understanding. Husserl agreed that consciousness shapes our experience, but believed we could systematically explore this by studying how consciousness works, helping us to clarify concepts and understand the conditions needed for knowledge. Unlike Kant, Husserl didn't claim that things in themselves are unknowable. Phenomenology steps away from questions about the existence of an external reality. It doesn't confirm or deny whether objects exist, but instead focuses on how they appear to us. This setting aside, known as the phenomenological reduction, or epoche, allows for a clear look at our experiences without getting weighed down by metaphysical worries. Gödel appreciated this approach because it avoided both naive realism and extreme skepticism. It didn't simply assume we perceive reality as it is, nor did it insist that we can't know anything beyond our own experiences. Instead, it looked at the relationship between our consciousness and objects, exploring how meanings are formed and how knowledge is organized. In terms of mathematics, this method was promising. By examining how we engage with mathematical concepts, for instance, how we perceive numbers or sets, we could explore mathematical intuition, the direct understanding of mathematical ideas and their properties, through a phenomenological lens. This could support mathematical Platonism without relying on mysterious interactions between our minds and abstract entities. Gödel also believed that phenomenology offered the systematic method he'd always been searching for in philosophy. He felt that philosophy, should be as precise as mathematics, and that it should progress through careful analysis, not guesswork. Husserl's phenomenology promised this level of precision. It called for a disciplined study of consciousness, methodical descriptions of essential structures, and gradual explanation of concepts. In a draft lecture from 1961, Gödel mentioned that phenomenology isn't a science in the conventional sense. He thought of it more as a method or practice that creates a new level of awareness, enabling us to define the basic concepts we use for thinking or to uncover unknown ones. This perspective is quite remarkable. Gödel saw phenomenology as something transformative, altering how we think by making us mindful of the conceptual frameworks we typically ignore. He even connected phenomenology directly to mathematics, proposing that mathematical intuition isn't a mysterious talent, but a form of conscious focus on abstract concepts. By understanding how this focus or directedness works, phenomenology could illuminate the nature of mathematical knowledge. Math intuition deals with abstract things that aren't tied to physical space or time. These are ideal objects and structures our minds can recognize and understand. They're objective because their properties are constant and not our creations. This understanding helps solve the age-old question in mathematical Platonism about how we know them. We don't need to physically interact with mathematical objects to get them. We need to engage with them mentally. Our consciousness can figure out concepts by noticing truths in specific instances and picking out key features in ideas. That's how we discover mathematical truths, through grasping concepts like numbers, which then open up more necessary truths. Gödel argued that phenomenology also addresses the concept of mathematical evidence. What makes something evidence for a math statement? It's not through experimental observation, since math doesn't deal with the physical world. And it's not just about formal proof, since proofs rely on axioms that need their own justification. The main thing is intuitive evidence, when mathematical structures make sense on their own when viewed clearly. Once we fully understand a math concept, certain truths naturally come out. For example, once you get sets, the axioms of set theory become obvious. But it's crucial to separate real evidence from illusions or mistakes, which is where phenomenological methods help. By carefully examining how we think, looking at examples for common traits, and aiming for clear understanding, we can clarify our concepts. Mathematical intuition isn't flawless, but can get better with thorough phenomenological study. Husserl explored this early on, especially with arithmetic. He looked at how we think about numbers by grouping objects and finding shared traits. 3 apples, 3 chairs, 3 thoughts all show the number 3. We see something universal by comparing examples and finding commonality. Gödel admired Husserl's insights, but thought they didn't cover more complicated math topics. Gödel wanted to extend this approach to areas like set theory and transfinite numbers, believing it supported the reality of mathematical ideas. The connection between phenomenology and Platonism in Gödel's work is complex. Some argue he moved away from Platonism to focus on ideal meanings rather than abstract objects. Others believe phenomenology simply supported Platonism without changing its core. I think Gödel managed to balance these views. He supported mathematical realism, saying mathematical truths are objective and not just mental constructs. but he saw accessing that reality through ideal structures, not by perceiving separate objects. These structures have objective properties, apart from individual perceptions, and aren't typical objects. Instead, they're essences or meanings that consciousness understands. While that might sound tricky, think of a word's meaning. It's not physical, but still objective. The word triangle represents a three-sided shape, no matter what someone thinks. We get this by understanding, not by using our senses. Mathematical ideas are similar. Ideal meanings with objective truths that we can grasp with focused mental effort. This view finds a balance between nominalism, which dismisses universals as mere labels, and naive Platonism, which views abstract objects as tangible ones. Gödel's view combines phenomenology and realism, suggesting mathematical concepts exist as ideal meanings, beyond space and time, understandable by our minds, and not made up on a whim. A challenge with this approach is about shared understanding. If mathematical ideas are meanings our consciousness taps into, how do we all get the same ideas? What makes sure your understanding of a set matches mine? Without that, math could become personal, with everyone seeing it differently. Gödel addressed this using Husserl's concept of shared fundamental structures. Human consciousness seems to be alike, with the same intuitive forms and reasoning ability. When we closely examine concepts phenomenologically, we find underlying truths that are universal. The idea of a number isn't just personal, it's an ideal concept that's understandable by all, as long as we have the ability to grasp it. This stirs up more questions. Why are our brains so good at understanding math? Is there some inherent connection between our minds and mathematical truths? Gödel had an optimistic outlook, suggesting that reason lines up with reality because they both rest on rational principles. The universe clicks with math because it's grounded in those principles, and our minds can grasp these principles since reason dovetails into the same rational framework. This idea nods to Leibniz's concept of pre-established harmony, which Gödel admired, and also brings to mind Plato's notion that learning means recalling what the soul knew before entering a body. Gödel didn't fully endorse these specific ideas, but his views hinted in that direction. We can understand math because our consciousness and mathematical reality share a rational foundation. But people have critiqued phenomenology and how Gödel applied it. For starters, phenomenology can feel too subjective to truly back up objective knowledge. If we're only looking at our own consciousness, how can we be sure it mirrors reality? Also, phenomenological descriptions are often vague and open to various interpretations. Different thinkers can portray the same ideas in a lot of different ways. Where's the precision Husserl promised? Plus, the terminology used in phenomenology, like intentionality or noesis, isn't always clear and makes critical evaluation difficult. Gödel knew about these issues. He sometimes criticized Husserl for being a bit scatterbrained, favoring a more systematic approach. He also saw phenomenology as a work in progress, not a fully established science. But he trusted the method and believed that with careful work, it could deliver results. Mathematical phenomenology was a project for the future, not a settled system. Gödel aimed to apply it specifically by examining the concept of a set phenomenologically. When we really get what a set is, We see it as any collection defined by a specific property or condition. We know that sets can be part of other sets. The hierarchy of sets doesn't stop. It goes on forever. These insights come from clarifying the concept intuitively, not through experiments or trial and error. From this clarity, we can justify the axioms of set theory. They should straightforwardly convey what the concept of a set involves. If they aren't clear, then more clarity or new insights are necessary to deepen our understanding. This is how mathematical knowledge expands, by digging into concepts and bringing out their hidden structures. Gödel never fully developed this idea. He left behind drafts and notes, but published very little on phenomenology. His main ideas are known through talks with Hao Wang, revealed long after Gödel's passing. We can outline his position, but there's no detailed phenomenological theory of mathematics. Despite this, Gödel venturing into phenomenology marked a major philosophical leap. It was a try to bring together realism and rationalism to explain how reason can understand an objective reality without directly interacting with it. It offered a systematic way to explore consciousness and its structures, and it connected Gödel's mathematical work to a broader philosophical theme dealing with meanings, intentions, and the foundation of knowledge. Whether phenomenology can fulfill all this is still up for discussion. Many philosophers find it puzzling or doubt if it delivers on its promises. But Gödel diving in shows his commitment to uncovering solid philosophical methods and his openness to drawing from various intellectual backgrounds. He wasn't content staying only on the technical side of logic. His curiosity propelled him to grasp the essence of mathematical understanding, probe how the mind links with reality, and figure out the right path for doing philosophy. Phenomenology seemed to offer a way to reach these goals, even if it was an incomplete quest. Part 9. Broader philosophical commitments. Hao Wang once asked Kurt Gödel to sum up his philosophical perspective. Gödel's reply was concise. His philosophy was rationalistic, idealistic, optimistic, and theological. These words encapsulate his approach to life. By exploring what Gödel meant with each of these terms, we gain insight into the philosophical ideas driving his work in logic, mathematics, physics, and metaphysics. Let's start with rationalism. Gödel believed reason was humanity's finest ability, convinced that pure reason could reveal deep truths about the universe. This put him at odds with empiricists, who rely on sensory experiences for factual knowledge, and skeptics, who doubt reason's capacity to access ultimate truths. For Gödel, mathematics demonstrated reason's power. Through rational insight, rather than what our senses perceive, we grasp concepts like infinity, abstract structures, and logical necessities. These truths arise from understanding concepts and knowing their implications. Gödel's rationalism extended beyond mathematics into metaphysics and theology. Consider the ontological argument, which attempts to prove God's existence through concept analysis. His belief that philosophical puzzles could be solved and that every real question had an answer highlights his faith in reason's power. While we may not have all the answers yet, reason, in theory, can uncover them. Gödel's rationalism had a Leibnizian influence. Leibniz claimed the world is fundamentally rational, governed by principles our reason can unravel, such as the principle of sufficient reason. nothing occurs without reason. Gödel believed reality adheres to a rational blueprint, a universe ruled by understandable laws, not randomness. Some might argue incompleteness theorems challenge rationalism by showing reason's limits. If formal systems can't prove every truth, doesn't that imply a flaw in reason? Gödel saw it differently. For him, incompleteness demonstrated reason's expansive reach. We aren't bound by mechanical rules. We can recognize truths that formal systems might miss and create new axioms to extend them. This limitless creativity of reason reveals its strength, not weakness. Next is idealism. We've mentioned Gödel's perspective on idealism in relation to time, how the flow of time and the past-future divide relate more to consciousness than to objective reality. However, Gödel's idealism was distinct from traditional German idealism. He wasn't idealistic about matter or physical substances. While space-time objectively exists, some things we perceive as real, like our sense of time or certain modal ideas, are tied to the observer rather than the objects themselves. This view aligns with Kant's transcendental idealism, though Gödel didn't agree with Kant's idea that things in themselves are unknowable. Gödel believed we could, through reason, see beyond appearances to grasp objective truths. Science and math are our tools for this insight. What's deemed ideal is not reality itself, but rather the structures our minds impose while experiencing it. Gödel's idealism also extended to mathematical objects. They aren't like physical objects. Instead, they are ideal structures our minds can understand. These truths are objective, grounded in ideal forms rather than tangible items. Then there's optimism, the third pillar. Gödel firmly believed every meaningful question could be answered and that progress in math and philosophy was possible. He thought the universe was rationally designed for minds to comprehend. This optimism remained strong despite his technical findings. Yes, formal systems have limitations, and some questions can't be resolved within specific frameworks. But we can always innovate, tweak systems, add new axioms, and foster greater intuition. No problem is truly insurmountable. His upbeat view spilled over into his thoughts on science and knowledge. Gödel thought science would keep pushing the boundaries to uncover deeper truths. Even if today's theories aren't the whole picture, that doesn't mean the truth is out of reach. It just means the journey continues. He predicted big developments in set theory, noticing the importance of large cardinals before others did, showing his belief in ideas eventually being discovered. Some might call this outlook naive, especially with all the terrible events of the 20th century, wars, dictatorships, and dangerous scientific advances. So why did Gödel remain so optimistic? Really, his outlook was about reason and knowledge more than about historical or human progress. He didn't think humanity was destined to become better morally, or that political issues would magically solve themselves. His hope centered on grasping truth, epistemology, and understanding what reality is, metaphysics, rather than focusing on history or politics. The fourth pillar of his beliefs was theology. Gödel had faith in God and an afterlife, believing there was more to reality than just the physical world. He discussed with friends how he was convinced of life after death through logical reasoning. He saw a rational structure in the world as pointing to a rational creator. His 14-point philosophy included the existence of other worlds, more intelligent beings, and the possibility of a detailed theology. Yet, his theological stance was more philosophical than religious. Despite being baptized Lutheran, he didn't really align with any specific faith group. He described his belief as theistic, not pantheistic, siding with Leibniz over Spinoza. This meant he believed in a personal God separate from the universe, rather than a divine presence within nature. How did his theological views influence his intellectual pursuits? They gave a metaphysical foundation to his rationalism and optimism. If there's a rational creator, then it makes sense that the universe is understandable, and truth can be discovered through reason. This belief drove his interest in philosophy and mathematics. Understanding mathematical patterns mirrored understanding the rational structure of creation. By clarifying concepts, he felt he was uncovering ideas rooted in the divine mind. While this might sound mystical, Gödel didn't see it that way. For him, these were logical conclusions drawn from contemplating mathematical truth, the universe's knowability, and what reason can achieve. His work on the ontological argument sought to show how belief in God could arise from properly understanding perfection and necessary existence. Critics might wonder if these four beliefs fit together. Can one be both rationalist and idealist? Rationalism looks for real, objective truth, while idealism suggests reality depends on the mind. But Gödel's take on idealism navigated around direct conflicts. He considered mathematical and physical structures real and only leaned toward idealism for parts of experience, like time's passage. Is it possible to be hopeful about reason despite the implications of incompleteness theorems? Sure, if those theorems highlight reason's creativity rather than limits, formal systems may be incomplete, but reason can go beyond any set framework. Can one be both a rational thinker and hold theological views? Certainly, if theology is based on arguments and not just faith or revelation. Gödel's theological outlook was deeply philosophical, even if it went beyond what many philosophers think is provable through reason. Now, let's explore more about Gödel's philosophical perspective as shown in his writings and discussions. He championed the power of conceptual analysis as the right path in philosophy. Instead of relying on empirical studies or building speculative theories, philosophy should break down and clarify concepts, exploring their meanings and implications carefully. Phenomenology offered a method for such analysis, though he aimed beyond any single strategy. Gödel believed many philosophical arguments came from unclear or confused concepts. By clarifying how we understand causation, time, existence, and truth, old problems could either disappear or become easier to tackle. This focus on clear concepts connected him to analytic philosophy, even though he had bigger ideas than most about what conceptual analysis could accomplish. Gödel had this huge idea that all kinds of knowledge were connected. For him, math, physics, philosophy, and theology weren't just separate disciplines. They all fit together like pieces of a giant puzzle striving to decode reality. You'd see math appear in physics raising philosophical questions, and philosophy using math's precision. This was Gödel's view, a novel approach back in the 20th century when everyone was busy dividing everything up. He also strongly believed that there was an objective truth in all these areas. To him, mathematical truths, scientific facts, morals, and even theological truths were objective, even if some were harder to grasp. It didn't mean we had all the solutions, just that they were out there waiting to be uncovered. He wasn't into weaving convenient tales or sticking to social norms. He wanted to uncover the real deal. This way of thinking set him apart from the idea that truths were merely social constructs or relative. Gödel wasn't swayed by the logical positivist's notion that only verifiable things were worth accepting. Truths like those in math and philosophy might be tough to test, but he believed they were important. He dismissed the idea that logic and math were arbitrary conventions, asserting they were discoveries. He didn't agree with seeing scientific theories as mere tools. He thought they depicted reality. These beliefs often clashed with popular philosophical ideas. He hung out with the Vienna Circle folks who championed logical positivism. Yet he quietly opposed their core concepts. He shared his ideas cordially, but held firmly to realism and rationalism. His famous incompleteness theorems were ironically viewed by many as supporting positivism because they identified limits in formal systems. Yet Gödel saw them as evidence that truth was larger than what could formally be proven. Another intriguing aspect of Gödel's view was his idea of math and reality being intertwined. He believed mathematical structures weren't just useful for explaining the universe. They were integral to its foundation. This hinted at a universe steeped in mathematics. So, when scientists used math to describe the universe, it wasn't just about language for him. It was because the universe itself was fundamentally mathematical. This perspective had a Pythagorean or Platonic vibe, and he embraced that. Modern physics even kind of aligns with this. Equations in quantum mechanics and general relativity do more than just explain mechanics. They uncover the very essence of nature. Math permeates particles and space-time. This viewpoint suggests that studying math is a route to understanding the universe itself. For Gödel, working in areas like logic and set theory wasn't just number crunching. It was about connecting with something deep and real within the universe's structure. It's also worth noting Gödel's belief in progress. Even while acknowledging persistent, unresolved issues, he believed our understanding was advancing. We know more now than people did long ago, and future generations will surpass us too. This progress wasn't automatic, though. It depended on continuing rational thought. What drives this progress? New ideas, methods, and sometimes groundbreaking insights from people like Gödel. In philosophy, progress was harder due to its contested and abstract nature, but he was confident it was achievable. Philosophers can actually make progress by using solid techniques like phenomenological analysis, logical formalization, or thoughtful argumentation. Philosophy isn't just a mishmash of random opinions. It's a continuously evolving exploration where new thinkers build upon previous ideas. This belief in progress set God apart from postmodern skeptics who see philosophy as never-ending interpretation without any real cumulative knowledge. He also differed from historicists who feel that philosophical ideas are so rooted in their cultural contexts that later thinkers can't truly improve upon them. Gödel believed that truth is timeless and that reason from any era can come closer to it. Wrapping up this segment, let's consider if God's broader philosophical vision really holds together. Can commitments like rationalism, selective idealism, optimism, theology, objectivism, and progressivism consistently coexist? There are some obvious tensions. Rationalism doesn't sit well with idealism. If idealism suggests that reality depends on the mind, then being optimistic about the power of reason hits a stumbling block with concepts like incompleteness and undecidability. Using rational arguments for theology might seem overly confident to many, but there's a common thread. All these beliefs arise from a central idea. The rational structure of reality can be understood through thought. Mathematical truths are objective because mathematical structures are real. Physical laws make sense because the universe is based on rational principles. Progress is within reach because reason can delve deeper into this rational order. God is believed to exist because, in a rational universe, there must be maximal perfection. Time is seen as ideal because it doesn't have the structure of relativistic space-time, according to reason. Whether this outlook stands the test of time is open for debate. Many philosophers and scientists have dismissed some or all of these ideas. Empiricists argue that reason alone can't access substantial truths. Naturalists reject both theology and metaphysical musings. Anti-realists in math question the objective existence of mathematical structures. Presentists contest the idea of temporal idealism. Yet, God's perspective is both intriguing and attractive. It seriously considers the reality of abstract structures and the human mind's capacity to understand them. It challenges the notion of reducing math to mere formalism or convention. It seeks unity and coherence across disciplines rather than accepting fragmentation. It emphasizes that knowledge and truth are fundamentally important. Getting to the truth is more than just helpful. It's intrinsically valuable. This view of philosophy fueled God's technical contributions, giving them purpose. He wasn't merely proving theorems, he was exploring the structure of mathematical reality. He wasn't simply solving logical puzzles, he was illuminating the connection between truth and proof. He wasn't just discovering new cosmological solutions, he was examining the nature of time. Every technical achievement contributed to the larger goal of understanding reality through reason. Part 10. Legacy and Influence. Kurt Gödel left this world on January 14, 1978, at 71. In his final days, his fear of being poisoned led him to stop eating, ultimately causing his death from malnutrition and severe weight loss. It was a tragic ending for such a brilliant mind of the 20th century. Yet, the mark he left on fields like mathematics, logic, computer science, physics, and philosophy remains strong even today. Gödel's influence is vast. Just his incompleteness theorems alone assure him a spot among the greats of modern thought, shifting how mathematicians and philosophers view the foundations of math. But Gödel did so much more. He proved the completeness theorem, developed ideas about the constructible universe, found cosmic solutions related to rotating universes, crafted the dialectica interpretation, and made major strides in set theory, proof, theory, and logic. Few thinkers have so profoundly impacted so many areas. Let's look at his impact on different fields. In mathematics, Gödel's incompleteness theorem showed math couldn't be completely formalized, ending the dream of reducing math to mere symbol manipulation. Yet this also opened new avenues. Mathematicians started to explore which statements were independent of which axioms and examine the logical hierarchy and relationships between foundational systems. Set theory, after Gödel, became a fertile ground for studying infinite concepts. His work on constructibility and the continuum hypothesis kicked off studies on why some phenomena are independent. Paul Cohen's forcing technique expanded on Gödel's insights and became a central tool, especially with large cardinal axioms, which Gödel had anticipated would be crucial to set theory. Because of Gödel's insights into the inherent incompleteness and independence, there's a growing quest to understand which statements need specific axioms. The field of model theory, which looks into formal languages and their meanings, largely springs from Gödel's completeness theorem. His methods for constructing models have become standard practice now. The Löwenheim-Skolem theorem, compactness, and research into non-standard models can all be traced back to Gödel's foundational work. Modern model theory owes much of its structure to his groundbreaking ideas. Proof theory, too, owes a lot to Gödel. Though Hilbert initiated it, Gödel's incompleteness theorems made everyone rethink proof theory's potential. Insights into consistency, the strength of systems, ordinal analysis, and the hierarchy of provability grew from the realization that you can't prove consistency from within a system, only from a stronger one. Gödel's speed-up theorems, showing that some proofs need much longer expressions in weaker systems, opened new avenues in logic. Using arithmetic to examine logical syntax, Gödel numbering became vital across mathematical logic and computability theory. Plus, his diagonal argument inspired many new discoveries. Gödel's achievements have transformed how logicians handle formalization and metamathematical reasoning. In the realm of computer science, Gödel's influence is equally deep, even if it's sometimes more indirect. His incompleteness theorems are directly linked to computability theory. Alan Turing built on Gödel's ideas to craft the beginnings of computation theory. The halting problem, which shows that no algorithm can always decide if programs finish running, ties closely to incompleteness. Both hinge on self-referential setups to demonstrate limits within formal systems. These intersections between logic and computing laid the groundwork for many ideas. The Church-Turing thesis, positing that what's computable is Turing computable, drew from Gödel's insights on the limits of formalization. Computational complexity theory, which deals with how much time and space problems need, uses approaches rooted in Gödel's encoding techniques. Automated theorem proving has to work around constraints, highlighted by Gödel's theorems. No algorithm can verify all true statements, nor confirm if some statements are independent of a given set of axioms, thus shaping the nature of automated reasoning systems. Even with these limits, there's been some remarkable progress. Nowadays, proof assistants can validate really complex mathematical proofs, but they still require human guidance since they can't create these proofs on their own. Those big philosophical debates about AI we've mentioned are also tied to Gödel's work. Can machines truly think? Is it possible for computation to fully mimic human intelligence? The Lucas-Penrose arguments, which rely on Gödel's theorems, might not be entirely convincing, but they've definitely inspired a lot of exploration into these questions. Today's AI research is grappling with ideas like creativity, insight, and understanding, all linked to what the incompleteness theorems reveal about formal systems versus human thought. In physics, even though Gödel's rotating universe solutions don't align with our actual universe, they've still had a significant impact. They demonstrated that general relativity can produce some really puzzling causal structures, prompting vast research into causality in curved spacetime, the idea of chronology protection, and the nature of spacetime itself. Physicists often ponder if spacetimes contain closed time-like curves and the physical laws that might prevent them. More broadly, Gödel's insights on relativity touch on fundamental questions about time, determinism, and the structure of spacetime. His idea that relativistic cosmology supports temporal idealism sparked debate among philosophers and physicists about the nature of time and general relativity. The discussions between those who view spacetime as a concrete entity and those who see it as relational, or between eternalists and presentists on the nature of time, all relate back to issues Gödel raised. Theoretical physics has also been influenced by incompleteness. Some physicists wonder if questions surrounding quantum gravity or string theory might be undecidable in a formal way. Others are investigating whether the very essence of physical law might be incomplete in a Gödel-like manner. Even though these ideas are still being debated and not definitively proven, they illustrate how Gödel's ideas continue to inspire new research paths. In philosophy, Gödel's impact is huge. His work revolutionized the philosophy of mathematics. The debate among Platonism, formalism, and constructivism became much more intense after Gödel showed that truth transcends provability. His support for mathematical realism, backed by technical arguments, gave Platonism a boost among philosophers who might have otherwise dismissed it. His influence on the philosophy of logic is equally significant. He prompted new considerations regarding the interplay of syntax and semantics, the role of proof versus truth, and the distinction between first-order and higher-order logic. The field of modal logic, especially concerning necessity and possibility in his ontological proof, also expanded after Gödel. In epistemology, Gödel's incompleteness has prompted deep reflection. If our formal systems aren't complete, how do we really know things? What role does intuition play in knowledge acquisition? Can reasoning alone justify beliefs in abstract domains? These were big questions even before Gödel, but they took on new dimensions after his theorems. Metaphysics has also been intrigued by Gödel's thoughts on time, possibility, and abstract entities. His rotating universe suggestion reignited the debate on whether time is real or just a concept. Discussions about mathematical entities and our understanding of them frequently reference his work. And although his ontological argument doesn't have widespread support, it rekindled interest in ontological proofs. In philosophy of mind, Gödel presents challenging questions about whether human thought can be completely mechanized in light of incompleteness. While Gödel himself was cautious about drawing overly bold conclusions, his work is a key reference point in debates about computationalism, understanding, and whether there's a non-algorithmic aspect to consciousness. Let's sort out some common mix-ups about Gödel's work that have popped up in both pop culture and scholarly areas. These errors sort of twist his legacy and confuse what he really proved. First off, some people think the incompleteness theorems claim certain things can't be known, but that's off base. Actually, The theorems reveal that within certain formal systems, some truths can't be proven. That doesn't mean humans are unable to know them. It's about the limits of formal proof, not human understanding. We can recognize Gödel's sentences as true through informal reasoning. We can't prove every truth using a set of rules and axioms. One common misunderstanding is that incompleteness makes math seem uncertain or makes mathematical truth seem subjective. That's just not right. Gödel himself believed in objective mathematical truths and showed that truth exists independently of what can be formally proven, highlighting that mathematical truths are out there on their own, beyond our formal systems. Incompleteness doesn't make math unstable. It emphasizes its endless complexity. Another misconception is that Gödel proved human minds aren't like machines. This isn't accurate either. While Gödel had doubts about mechanistic ideas, he didn't claim he had proof for this. The Lucas-Penrose arguments, which tried to use incompleteness to argue against a mechanistic view of the mind, have been heavily criticized and mostly dismissed. The connection between incompleteness and the nature of the mind is still a complex philosophical debate. There's also the misconception that incompleteness universally shows all systems have limits. That's exaggerated. Incompleteness matters for consistent formal systems that can handle basic arithmetic. It doesn't automatically apply to fields like law, science, or theology unless they're organized in a comparable way. Using incompleteness outside math needs strong backing, not just casual references. Then there's the idea that Gödel's rotating universe proves time travel is possible or questions time's existence. That's misleading. The rotating universe is a solution to Einstein's equations, but it doesn't represent our universe. It shows general relativity can allow such cases, but whether time travel is possible or time is just a notion are entirely different questions that need more than Gödel's model. Another incorrect belief is that Gödel's ontological proof undeniably shows God's existence. This is contentious. The proof holds up logically if the axioms are agreed upon, but these axioms are debatable, leading to issues like modal collapse. Most philosophers reject it, though some attempt to defend modified forms. At best, it shows what comes if you accept specific ideas about perfection and necessity. These myths are important because they distort Gödel's work. When journalists, communicators, or even scholars casually mention Gödel to support major claims about knowledge limits or AI, they misrepresent his work. Gödel's actual contributions are impressive without needing to stretch their implications. His mix of technical brilliance and profound philosophical insight made him a unique intellectual force. Students and colleagues remember his meticulous and sometimes excessively cautious nature. He questioned assumptions others took for granted and demanded clear, precise expressions, which made him a tough but highly valuable conversationalist. Significant advances in logic and foundational studies often arose from addressing the questions and challenges Gödel introduced. After the 1940s, Gödel published less frequently, choosing to work on problems until he was fully satisfied with the results. This perfectionism meant some of his important work wasn't published until it got discovered in his notes after he died. Still, what he did publish was consistently exceptional and enduring. His personal quirks, such as occasional paranoia, health worries, and greater reclusiveness sometimes overshadowed his intellectual accomplishments in biographies. However, those who knew him well recognized his brilliance, profound philosophical thinking, and kind nature. He guided many students, maintained extensive correspondences with other thinkers, and generously engaged with ideas, even those he disagreed with. Why should we care about Gödel's work today? Well, the big questions he tackled are still up for grabs. Take the continuum hypothesis, for example. It hasn't been solved using the usual axioms. Gödel's search for new axioms is an ongoing adventure. The philosophical discussions about incompleteness are still sparking debates. His work isn't just a dusty old chapter in history, it's a key player in our quest for answers. As computing becomes more central in science and our everyday lives, Gödel's ideas about limits have real-world punch. Understanding what's computable, what can be verified, and what algorithms can decide traces right back to his theories on incompleteness and computability. And with AI stepping up, questions about machine smarts versus human understanding bring us back to Gödel's theorems. As AI grows, knowing where it stumbles becomes crucial. Gödel's work helps us see what formal systems can do and where human insight still matters. We've yet to crack major math and physics foundations. Just look at string theory's challenges with testing and uniqueness, or quantum mechanics interpretation dilemmas, and set theory's axiom debates. Gödel's knack for combining rigorous math with foundational questions is still super relevant. Beyond that, his passion for a unified, rational look at tough questions resonates with those tired of narrow specialties. Gödel showed how technical chops and philosophical thinking elevate each other. His legacy teaches us meaningful inquiry requires mastering formal systems and a broad understanding. Now, let's think about where Gödel's impact hasn't been as strong. Though his philosophical dive into phenomenology was big for him, it hasn't made as much of a splash. Most mathematicians and logicians aren't aware of his interest in Husserl, and although some philosophers chat about his views on time, they haven't transformed physics the way his logic has. His theological curiosities are often seen more as niche topics rather than reshaping mainstream discussions. The ontological proof is sometimes treated as more of a fun logical puzzle than a serious case for God's existence. His confidence in rational philosophy gets side-eye from today's more skeptical philosophical vibes. Still, there seems to be a revival of interest in Gödel's wider philosophical ideas. New research digs into the connections between his technical work and philosophy. With the release of his collected writings, some hidden gems of his thoughts are being discovered. There's a growing number of philosophical studies and biographies exploring his thinking. To sum things up, consider what Gödel's life and work stand for. He showed us that deep-dive formal methods can shine a light on the biggest questions about knowledge, truth, and reality. He blended technical brilliance with philosophical depth. His work makes it clear that foundational questions are not just abstract. They're key to grasping how we think and the boundaries of knowledge. Gödel wasn't one to follow the crowd. He championed mathematical Platonism in the age of formalism, idealism about time against popular thinking, and rational theology when metaphysics was out of favor. He stayed true to what he believed, even if it wasn't trendy. His mix of rigorous logic and gutsy ideas made him stand out. He wouldn't make claims without solid backing, yet always remained eager to explore the ideas others overlooked. He took age-old philosophical problems seriously and applied modern mathematical tools to them. His method combined classical philosophical inquiries with current formal techniques. While he's best known for the incompleteness theorems, Gödel's legacy runs deeper, showing us that math has limitless layers, formal systems have built-in bounds, and truth goes beyond what can be proven. He brought innovative ideas to set theory and cosmology, stood up for mathematical Platonism from both a philosophical and technical angle, and explored how logic, math, physics, and metaphysics are connected. Most significantly, Gödel demonstrated that reason could tap into the core structures of reality while still recognizing its own limits. The incompleteness theorems aren't reasons to lose hope, but rather gateways to fresh opportunities. There will always be more truths to discover, more principles to grasp, and more concepts to make clear. Math and philosophy are never-ending journeys that require ongoing creativity and insight. In this sense, Gödel's work embodies a deep sense of humanism. He showed that human thought can't be entirely broken down or explained by formal systems. Real understanding is more than just following rules. It involves intuition, judgment, and creativity that go beyond simple algorithms. Even though machines can prove theorems and handle symbols, true mathematical understanding involves grasping concepts and recognizing truths that no routine process can produce. This is especially important now in an age where computation and formal methods are widespread. Gödel reminds us that while accuracy and formalization are essential, they can't replace human thinking. They help clarify what we already know, but can't create understanding by themselves. The insights crucial to mathematics and philosophy stem from humans, something no computer can replicate without entirely new principles. Kurt Gödel's intellectual journey, from his incompleteness theorems through Platonism, set theory, cosmology, phenomenology, and theology, marks one of the most remarkable intellectual achievements in history. His work had a transformative impact on many fields and continues to offer insights long after his death. Understanding what he discovered, what he believed, and why he pursued particular questions enriches our grasp of mathematics, logic, philosophy, and the essence of rational thought. His legacy is not fixed. Continuing discussions about the implications of incompleteness, the viability of Platonism, the nature of time, the future of artificial intelligence, and the essence of mathematical truth show that the questions Gödel raised are too profound for straightforward answers. He encouraged us to think deeply about foundational ideas, to mix rigorous thinking with significant concepts, and to trust in reason's ability to unveil truths despite inherent incompleteness. That's the ultimate takeaway. Incompleteness isn't failure, but an admission that math is more intricate than any finite set of principles. The journey to deeper understanding never truly ends, but each step opens new views. Gödel charted some of that map with exceptional clarity, illustrating both the extent of reason and the vast possibilities yet to be explored. His life's work is a tribute to seeking truth through rational inquiry, challenging, profound, and endlessly open-ended.